Something is moving in the dark. A ghost burning through the void. Its name is Mira, a red giant, a dying star, and it's leaving behind a trail, 13 light-years long, like a cosmic comet bleeding across the galaxy. Astronomers once thought stars died quietly. Mira shattered that idea. When NASA's ultraviolet eyes locked onto it, they saw a glowing ribbon, a stellar scream stretching farther than our closest stars. It was as if the universe had been hiding a secret, one it could no longer contain. Mira is a remarkable star located approximately 300 light-years from Earth in the constellation Cetus. This celestial object holds great significance in the field of astronomy for several reasons. Firstly, Mira is the prototype of a class of variable stars known as Mira variables. These stars are characterized by their pulsating nature, dramatically changing in brightness over long periods. Mira itself varies in brightness over a cycle of about 330 days, at times becoming bright enough to be visible to the naked eye, while at other times fading to the point where it requires a telescope to be seen. The study of Mira has provided astronomers with valuable insights into the late stages of stellar evolution. Mira is a red giant star, nearing the end of its life. As it pulsates, it sheds its outer layers into space, creating a surrounding envelope of gas and dust. This process is crucial for understanding how stars enrich the interstellar medium with heavy elements, contributing to the chemical evolution of galaxies. Furthermore, observations of Mira have revealed an unexpected feature: a comet-like tail stretching an astonishing 13 light-years behind the star as it moves through space. This discovery, made by NASA's Galaxy Evolution Explorer in 2007, has challenged our understanding of how stars interact with their environment and opened up new areas of research in stellar astrophysics. Mira, also known as Omicron Ceti, was first discovered as a variable star in 1596 by Dutch astronomer David Fabricius. While observing the planet Mercury, Fabricius noticed a star that appeared to change in brightness over time. This star, which would later be named Mira, meaning wonderful or astonishing in Latin, was the first known variable star. Fabricius initially thought he had discovered a nova, a star that suddenly increases in brightness. However, he later observed that the star's brightness fluctuated periodically, fading and brightening over time. This discovery was groundbreaking, as it challenged the prevailing belief that stars were unchanging and eternal. The true nature of Mira's variability was not fully understood until the early 20th century. Astronomers now know that Mira is a type of pulsating variable star, specifically a long-period variable. These stars expand and contract over time, causing changes in their brightness that can be observed from Earth. Mira continues to be an object of fascination for astronomers and stargazers alike. Its discovery marked the beginning of our understanding of stellar variability and paved the way for further studies of the dynamic nature of stars in our universe. Mira, a remarkable star in the constellation Cetus, received its name from the Latin word meaning wonderful or astonishing. This name was bestowed upon the star by Johannes Hevelius in 1662, though the star's variable nature had been noted by earlier astronomers. The name perfectly captures the essence of this celestial object, as Mira is indeed a wonder to behold. It is a long-period variable star, which means its brightness changes dramatically over time. For most of its 11-month cycle, Mira is too faint to be seen with the naked eye. However, at its peak, it can become one of the brightest stars in the night sky. This dramatic change in brightness is what made Mira so astonishing to early astronomers. They watched in awe as this star seemed to appear and disappear regularly, like a cosmic beacon pulsing in the depths of space. The star's behavior was so unusual that it became the prototype for an entire class of variable stars, now known as Mira variables. Today, we understand that Mira's fluctuations are caused by changes in its size and temperature as it nears the end of its life cycle. As it pulsates, expanding and contracting, its brightness varies accordingly, continuing to live up to its wonderful and astonishing name. Mira stands out as a remarkable celestial object in our night sky. This pulsating variable star, located about 300 light-years from Earth in the constellation Cetus, exhibits extraordinary behavior that sets it apart from its stellar counterparts. Unlike most stars we observe, Mira's brightness fluctuates dramatically over time. It cycles between being visible to the naked eye and fading to near invisibility over a period of about 11 months. This dramatic change in luminosity is caused by Mira's pulsations as it expands and contracts, alternately cooling and heating its outer layers. Another distinctive feature of Mira is its colossal size. As a red giant star nearing the end of its life, Mira has swollen to nearly 400 times the size of our Sun. If placed at the center of our solar system, it would engulf Mercury, Venus, Earth, and even extend beyond the orbit of Mars. Perhaps most intriguingly, Mira is leaving a trail of stellar material in its wake as it hurtles through space. This cosmic wake, stretching an astonishing 13 light-years behind the star, was discovered by ultraviolet observations. It provides astronomers with a unique opportunity to study stellar evolution and the enrichment of the interstellar medium in real time, making Mira a true cosmic marvel. Mira, also known as Omicron Ceti, shines in the constellation Cetus, the Whale. This remarkable star can be found in the southern part of Cetus, near the celestial equator. Stargazers in both the northern and southern hemispheres can observe Mira, though it is more easily visible from southern latitudes. As a variable star, Mira's brightness changes dramatically over time. At its peak, it can be one of the brightest stars in Cetus, rivaling the constellation's alpha star, Deneb Kaitos. However, during its dimmer phases, Mira becomes invisible to the naked eye, requiring binoculars or a telescope to spot. Mira's location within Cetus is significant, as this constellation is associated with the sea monster from Greek mythology. The star's pulsating nature, alternating between bright and dim states, adds to the mystique of this celestial region. Observers can find Mira by looking for the distinctive shape of Cetus, which resembles a fish or whale, and locating the star within its southern portion. Mira, also known as Omicron Ceti, is a fascinating star located approximately 420 light-years from Earth. This distance means that the light we see from Mira today actually left the star 4 centuries ago. To put this into perspective, when the light we now observe from Mira began its journey, Galileo was just beginning to use his telescope to study the night sky. Mira is a binary star system consisting of a red giant star and a smaller companion. The main star, Mira A, is a pulsating variable star that dramatically changes in brightness over a period of about 11 months. At its brightest, it can be visible to the naked eye, while at its dimmest, it requires a telescope to observe. The vast distance between Earth and Mira presents both challenges and opportunities for astronomers. While it makes detailed observations more difficult, it also allows scientists to study a star system that is quite different from our own, providing valuable insights into stellar evolution and the life cycles of stars. Mira, a remarkable variable star known for its dramatic changes in brightness, is located in the constellation Cetus. Cetus is often referred to as the Whale or the sea monster in celestial mythology. This large constellation sprawls across the night sky in the northern hemisphere's autumn and winter months. Cetus is part of the ancient Greek tradition of constellations, and it holds a significant place in the story of Perseus and Andromeda. Within this expansive star pattern, Mira stands out not for its constant brilliance, but for its captivating cycle of brightening and dimming. As the first known variable star, Mira has played a crucial role in advancing our understanding of stellar evolution. Its pulsating nature, with a period of about 330 days, has fascinated astronomers for centuries. At its brightest, Mira can be easily seen with the naked eye, while at its dimmest, it requires a telescope to observe. The presence of Mira in Cetus adds an extra layer of intrigue to this constellation, making it a favorite target for both amateur stargazers and professional astronomers alike. Its rhythmic dance of light continues to provide valuable insights into the life cycles of stars and the dynamic nature of our universe. Mira, also known as Omicron Ceti, earned its nickname the Wonderful Star due to its extraordinary behavior. This remarkable celestial object is a pulsating variable star that undergoes dramatic changes in brightness over a period of about 11 months. At its peak, Mira can shine as brightly as a star of the second or third magnitude, easily visible to the naked eye. However, during its dimmer phases, it fades to such an extent that it becomes invisible without the aid of a telescope. This dramatic fluctuation in brightness captivated astronomers for centuries. The star's name, Mira, comes from the Latin word for wonderful or astonishing, reflecting the awe it inspired in early observers. Its discovery as a variable star is credited to David Fabricius in 1596, making it one of the first known variable stars apart from novae and supernovae. Mira's variability is caused by its nature as a red giant star nearing the end of its life. As it pulsates, expanding and contracting, its outer layers cool and heat, resulting in the observed changes in brightness. This process also causes Mira to shed its outer layers, creating a surrounding shell of gas and dust that contributes to its fascinating appearance. The study of Mira and similar stars has greatly enhanced our understanding of stellar evolution and the life cycles of stars. Its predictable yet dramatic changes continue to make it a favorite target for both amateur and professional astronomers, truly living up to its reputation as the wonderful star. Mira, also known as Omicron Ceti, is a remarkable variable star that captivates astronomers and stargazers alike. At its brightest, Mira can reach a magnitude of about 2.0, making it easily visible to the naked eye. This level of brightness is comparable to the stars in the Big Dipper, a well-known asterism in the night sky. What makes Mira truly fascinating is the dramatic change in its apparent brightness over time. During its dimmer phases, the star fades to around magnitude 10, becoming invisible without the aid of a telescope. This significant variation occurs over a period of about 11 months, earning Mira its name, which means wonderful or astonishing in Latin. The extreme changes in Mira's brightness are due to its nature as a pulsating variable star. As it expands and contracts, its surface temperature and size fluctuate, causing the dramatic shifts in luminosity we observe from Earth. This pulsation is a natural part of Mira's life cycle as a red giant star, showcasing the dynamic nature of stellar evolution. Mira's peak brightness serves as a celestial beacon, drawing attention to the ever-changing nature of our universe and reminding us that even the seemingly constant stars above us are in a state of constant flux. Mira, also known as Omicron Ceti, is a fascinating star that captivates astronomers with its remarkable variability. This red giant star undergoes a regular cycle of brightening and dimming that spans approximately 332 days. During this period, Mira's brightness can change dramatically, sometimes becoming visible to the naked eye, and at other times fading to the point where it requires a telescope to observe. At its brightest, Mira can shine as brilliantly as a third-magnitude star, making it easily visible in the night sky. However, when it dims, it can fade to as faint as a 10th magnitude, becoming practically invisible without the aid of powerful telescopes. This extreme range in brightness, covering about 7 magnitudes, is what makes Mira such an intriguing target for both amateur and professional astronomers. The variability of Mira is caused by pulsations in the star's outer layers. As a red giant nearing the end of its life, Mira has swollen to an enormous size. These pulsations cause the star to expand and contract, changing its surface temperature and luminosity. When the star expands, it cools and dims. When it contracts, it heats up and brightens. Mira's predictable cycle has made it the prototype for an entire class of variable stars known as Mira variables. These long-period variable stars all exhibit similar characteristics, with regular cycles of brightness variation lasting between 80 and 1,000 days. Studying Mira and stars like it helps astronomers better understand the late stages of stellar evolution and the processes that occur in aging stars. Variable stars are celestial objects that change in brightness over time. Unlike most stars that maintain a relatively constant luminosity, these cosmic beacons fluctuate in their light output, creating a mesmerizing celestial dance visible from Earth. There are several types of variable stars, each with its own mechanism for brightness variation. Some stars pulsate, expanding and contracting rhythmically, which causes their luminosity to increase and decrease. Others are part of binary systems where one star periodically eclipses the other, resulting in regular dips in brightness. Cepheid variables are particularly important in astronomy. These stars pulsate with a precise relationship between their period of variation and their intrinsic brightness, making them invaluable tools for measuring cosmic distances. By observing the pulsation period of a Cepheid variable, astronomers can determine its true luminosity and, in turn, calculate its distance from Earth. Studying variable stars provides crucial insights into stellar evolution, galactic structure, and the fundamental physics governing our universe. As we continue to observe and analyze these flickering cosmic beacons, we uncover new layers of understanding about the dynamic and ever-changing nature of our night sky. Variable stars are celestial objects that captivate astronomers with their unique behavior. Unlike most stars that maintain a relatively constant brightness, variable stars experience noticeable changes in their luminosity over time. These fluctuations can occur rapidly, within hours or days, or slowly over months or even years. The causes of these brightness variations are diverse. Some variable stars pulsate, expanding and contracting due to internal pressure changes. This pulsation alters their size and temperature, resulting in periodic brightness fluctuations. Other variable stars exist in binary systems where two stars orbit each other. As one star passes in front of the other, it blocks some of the light, causing the overall brightness to dim temporarily. Cepheid variables are particularly significant in astronomy. These stars pulsate with a regular period that directly relates to their luminosity. This relationship allows astronomers to use Cepheid variables as cosmic distance markers, helping measure vast distances across the universe. Studying variable stars provides valuable insights into stellar evolution, structure, and composition. By observing their changing brightness patterns, scientists can uncover information about a star's mass, temperature, and internal processes, making variable stars crucial tools in our quest to understand the cosmos. Stars can become variable for several fascinating reasons. One common cause is pulsation, where a star expands and contracts rhythmically due to internal pressure changes. This pulsation alters the star's brightness as it changes size, creating a mesmerizing cosmic heartbeat visible from Earth. Another intriguing cause of stellar variability is the presence of star spots, similar to sunspots on our own sun. These darker, cooler regions on a star's surface rotate in and out of view, causing subtle fluctuations in the star's overall brightness. This phenomenon offers astronomers valuable insights into stellar rotation and magnetic activity. Binary star systems can also lead to variability. When two stars orbit each other closely, they can periodically eclipse one another from our perspective, causing regular dips in brightness. This dance of celestial bodies provides crucial information about stellar masses and sizes. Some stars become variable due to violent events like novae or supernovae. These explosive processes cause dramatic and often unpredictable changes in a star's brightness, sometimes increasing its luminosity by thousands or even millions of times. Such events not only alter the star itself, but also play a crucial role in enriching the surrounding space with heavy elements. Variable stars are celestial objects that change in brightness over time. These fascinating stars come in several types, each with unique characteristics and reasons for their variability. Pulsating variables are stars that physically expand and contract, causing changes in their brightness. Cepheid variables are a well-known subtype used as cosmic distance markers due to their predictable relationship between pulsation period and luminosity. RR Lyrae stars are another pulsating type, often found in globular clusters and useful for studying galactic structure. Eruptive variables undergo sudden increases in brightness due to violent events on their surfaces or in their atmospheres. These include flare stars, which experience unpredictable bursts of energy, and novae, where material accreted from a companion star ignites in a thermonuclear explosion on the surface of a white dwarf. Eclipsing binary stars are systems where two stars orbit each other, periodically blocking each other's light from our view. While not intrinsically variable, their apparent brightness changes as seen from Earth. Algol, also known as the Demon Star, is a famous example of this type. Cataclysmic variables involve a white dwarf and a companion star in a close binary system. Matter from the companion is drawn onto the white dwarf, leading to periodic outbursts. These stars can exhibit a range of behaviors, from small, frequent eruptions to rare, massive explosions known as supernovae. Astronomers classify variable stars based on the nature and cause of their brightness fluctuations. One major category is intrinsic variables, where changes occur within the star itself. These include pulsating variables like cepheids, which expand and contract regularly, causing rhythmic brightness changes. RR Lyrae stars, another type of pulsating variable, are older, less massive stars that show rapid brightness variations. Eruptive variables form another important class. These stars experience sudden increases in brightness due to violent events on their surfaces or in their atmospheres. Flare stars, for example, show unpredictable, short-lived brightness spikes caused by magnetic activity. Nova and supernova events, where stars undergo dramatic explosions, also fall into this category. Extrinsic variables, on the other hand, change in brightness due to external factors. Eclipsing binaries are prime examples, where one star periodically passes in front of its companion, causing a dip in overall brightness. Rotating variables are stars with uneven surface brightness or shapes that appear to change as they spin. Astronomers also classify variables based on their periodicity. Some stars show regular, predictable changes, while others vary irregularly or even in seemingly random patterns. By studying these diverse types of variable stars, scientists gain crucial insights into stellar evolution, galactic structure, and even the fundamental properties of our universe. Variable stars are cosmic beacons that offer astronomers invaluable insights into the universe. These celestial objects change in brightness over time, revealing crucial information about stellar evolution, galactic structure, and even the fundamental nature of the cosmos. By observing variable stars, scientists can determine crucial stellar properties such as mass, radius, and composition. This knowledge helps refine our understanding of how stars are born, live, and die. Some types of variable stars, like Cepheid variables, have a predictable relationship between their brightness and pulsation period. This relationship allows astronomers to use them as cosmic yardsticks, measuring vast distances across the universe with remarkable accuracy. Variable stars also play a vital role in testing and improving theoretical models of stellar physics. The pulsations and fluctuations observed in these stars provide a real-world laboratory for studying complex processes occurring inside stellar interiors, which are otherwise hidden from view. This knowledge not only enhances our grasp of stellar evolution, but also contributes to our understanding of galactic formation and structure. Furthermore, the study of variable stars has led to groundbreaking discoveries in cosmology. For instance, the use of Type Ia supernovae, a class of variable stars, as standard candles led to the shocking revelation that the expansion of the universe is accelerating. This discovery fundamentally altered our view of the cosmos and earned its researchers the Nobel Prize in Physics. As we continue to observe and analyze variable stars, we unlock new secrets about the universe and our place within it. Variable stars play a crucial role in advancing our knowledge of stellar evolution. These celestial objects exhibit periodic changes in brightness, providing astronomers with valuable insights into the internal structures and life cycles of stars. One of the most important types of variable stars is the Cepheid variable. These pulsating stars have a direct relationship between their luminosity and pulsation period, making them excellent cosmic distance markers. By studying Cepheid variables, scientists can measure vast distances across the universe, helping us map out the structure and scale of galaxies. Another significant class of variable stars is the RR Lyrae variables. These older, low-mass stars are found in globular clusters and provide clues about the age and composition of the earliest stars in our galaxy. Their pulsations allow astronomers to probe the internal structures of these ancient stellar populations, shedding light on the early stages of galactic evolution. Variable stars also help us understand the final stages of stellar life. For instance, studies of Mira variables, which are red giant stars nearing the end of their lives, reveal how stars shed their outer layers and enrich the interstellar medium with heavy elements. This process is crucial for the formation of new stars and planets, connecting the life cycles of individual stars to the broader evolution of galaxies. Astronomers employ a variety of sophisticated instruments to study variable stars, each offering unique insights into these fascinating celestial objects. Telescopes form the foundation of this research, with both ground-based and space-based observatories playing crucial roles. Optical telescopes capture visible light, allowing astronomers to track changes in brightness over time. These observations are often enhanced by charge-coupled devices, highly sensitive digital cameras that can detect even subtle variations in stellar luminosity. For a more comprehensive view, astronomers turn to spectroscopes. These instruments split starlight into its component wavelengths, revealing valuable information about a star's temperature, composition, and motion. By analyzing spectral changes, researchers can uncover the underlying causes of stellar variability, such as pulsations or binary star interactions. Space-based observatories like the Hubble Space Telescope and the Transiting Exoplanet Survey satellite have revolutionized the study of variable stars. Free from atmospheric interference, these advanced instruments can make extremely precise measurements of stellar brightness and detect minute fluctuations that might be missed by ground-based telescopes. Photometers, both on the ground and in space, are essential tools for measuring the exact amount of light emitted by variable stars. These instruments allow astronomers to create detailed light curves, graphical representations of how a star's brightness changes over time. By analyzing these curves, researchers can determine the type of variable star, its period of variation, and even estimate its distance from Earth. Our understanding of variable stars has undergone a remarkable evolution since their initial discovery. In the 16th century, astronomers first noticed that some stars seemed to change in brightness over time. This observation challenged the prevailing notion that stars were fixed and unchanging celestial objects. As observational techniques improved, astronomers began to catalogue and classify different types of variable stars. They discovered that some stars pulsate, expanding and contracting in regular cycles, while others vary due to eclipses by companion stars. The famous astronomer Henrietta Swan Leavitt made a crucial breakthrough in the early 20th century when she discovered a relationship between the period of pulsation and the luminosity of certain variable stars called Cepheid variables, and the fundamental physics of the cosmos. Amateur astronomers play a crucial role in variable star research, contributing significantly to our understanding of stellar behavior and evolution. These dedicated sky watchers monitor stars that change in brightness over time, providing valuable data to professional astronomers and astrophysicists. One of the most important contributions amateur astronomers make is in the field of long-term monitoring. Many variable stars change their brightness over periods ranging from hours to years, or even decades. Professional observatories often lack the resources to continuously observe these stars, but a network of amateur astronomers can provide consistent, long-term data sets that are invaluable for understanding stellar processes. Amateur astronomers also excel at discovering new variable stars. By systematically observing and recording the brightness of stars in specific regions of the sky, they can identify previously unknown variables. This work expands our catalogue of known variable stars and sometimes leads to the discovery of rare or unusual stellar phenomena. Furthermore, amateur astronomers often respond quickly to sudden changes in variable stars, such as unexpected outbursts or dimming events. Their ability to mobilize rapidly and provide immediate observations helps professional astronomers direct more powerful telescopes to study these events in detail, enhancing our knowledge of stellar behavior. Mira is a prime example of a long-period variable star, specifically classified as a pulsating variable. These fascinating stellar objects are known for their dramatic changes in brightness over extended periods. Mira itself, also called Omicron Ceti, is the prototype for an entire class of variable stars known as Mira variables. Mira variables are typically red giant stars nearing the end of their lives. They pulsate in size, alternately expanding and contracting over cycles that can last anywhere from 100 to 1,000 days. This pulsation causes significant changes in their luminosity, with Mira itself varying in brightness by a factor of around 1,000. What makes Mira particularly intriguing is the extent of its variability. At its brightest, it can be visible to the naked eye, shining as one of the more noticeable stars in the constellation Cetus. However, at its dimmest, it fades to a point where it requires a telescope to be seen. This dramatic change occurs over a period of about 330 days. The pulsations of Mira variables are driven by complex processes within the star itself. As the star expands and contracts, its outer layers heat and cool, changing the opacity of the stellar material. This interplay between the star's internal structure and its surface properties results in the mesmerizing dance of light we observe from Earth, making Mira and stars like it captivating subjects for both amateur and professional astronomers alike. Mira stands as a shining example of long-period variable stars, earning its status as the prototype for an entire class known as Mira variables. This remarkable star, located in the constellation Cetus, caught the attention of astronomers centuries ago due to its dramatic changes in brightness. Over a period of about 330 days, Mira's luminosity fluctuates by an astonishing factor of about 1,000, making it visible to the naked eye at its peak before fading to near invisibility at its dimmest. The pulsations that cause these dramatic brightness variations are a defining characteristic of Mira variables. These stars are typically red giants nearing the end of their lives, having expanded to enormous sizes. As they pulsate, their outer layers swell and contract, causing changes in temperature and radius that result in the observed brightness variations. Mira's consistent and extreme variability made it an ideal candidate for detailed study, allowing astronomers to identify and categorize similar stars. Its behavior became the benchmark against which other long-period variables are compared. This led to the recognition of a whole class of stars exhibiting similar properties, now collectively known as Mira variables. The study of Mira and its variable star cousins has provided valuable insights into stellar evolution, particularly the late stages of a star's life. By understanding Mira, astronomers have gained a better grasp of the processes that occur as stars age, swell, and eventually shed their outer layers, contributing to the enrichment of the interstellar medium. Mira variables are a fascinating class of pulsating stars that captivate astronomers with their dramatic changes in brightness. These long-period variable stars, named after the prototype star Mira in the constellation Cetus, are known for their striking visual displays. Currently, astronomers have identified and classified approximately 6,000 stars as Mira variables within our Milky Way galaxy. However, this number is constantly evolving as new observations and surveys uncover more of these intriguing celestial objects. Mira variables are typically red giant stars nearing the end of their stellar lives. They pulsate over periods ranging from about 80 to 1,000 days, causing their brightness to fluctuate by several magnitudes. This remarkable variation makes them stand out among other stars in the night sky, drawing the attention of both professional and amateur astronomers alike. The study of Mira variables extends beyond our galaxy. Astronomers have also detected these stars in nearby galaxies, including the Magellanic Clouds and the Andromeda Galaxy. As our observational techniques and technologies improve, we continue to discover more Mira variables, expanding our understanding of stellar evolution and the dynamics of aging stars across the universe. Mira variables are a fascinating class of pulsating stars that captivate astronomers with their dramatic changes in brightness. These stars, named after the prototype Mira in the constellation Cetus, are aging red giants nearing the end of their stellar lives. Their most striking feature is their extreme variability in luminosity, with brightness changes that can span several magnitudes over periods ranging from about 100 to 1,000 days. These long-period variable stars typically increase in brightness by 5 to 7 magnitudes during each cycle, which means they can become several thousand times brighter at their peak compared to their dimmest point. This remarkable fluctuation is visible even to the naked eye for some Mira variables, making them objects of interest for both professional and amateur astronomers. Mira variables are characterized by their cool surface temperatures and large, extended atmospheres. As they pulsate, these stars expand and contract, causing changes in their temperature and size. This pulsation is driven by periodic changes in the opacity of ionized helium in their outer layers, creating a self-sustaining cycle of expansion and contraction. Another defining characteristic of Mira variables is their mass loss. These stars are shedding their outer layers into space, creating expansive circumstellar envelopes rich in dust and molecular gas. This process plays a crucial role in enriching the interstellar medium with heavy elements, contributing to the chemical evolution of galaxies and providing material for future generations of stars and planets. Mira variables stand out among the diverse array of variable stars due to their distinctive characteristics and behavior. These pulsating stars, named after the prototype Mira in the constellation Cetus, are aging red giants nearing the end of their stellar lives. Unlike many other variable stars, Mira variables exhibit dramatic and regular changes in brightness, with their luminosity often increasing by several magnitudes over periods ranging from about 100 to 1,000 days. What sets Mira variables apart is the extreme nature of their pulsations. These stars can swell to nearly double their size and then contract again, causing their surface temperature to fluctuate significantly. This process leads to remarkable changes in their visual brightness, sometimes becoming up to 10,000 times brighter at their peak compared to their dimmest state. Such pronounced variations are rarely seen in other types of variable stars. Another unique aspect of Mira variables is their long-term instability. While their pulsation periods remain relatively consistent, the amplitude of their brightness changes can vary from cycle to cycle. This unpredictability adds an element of intrigue for astronomers studying these stars. Additionally, Mira variables are known for their mass loss, shedding their outer layers into space and creating shells of gas and dust around them. The study of Mira variables provides valuable insights into the late stages of stellar evolution for low to intermediate mass stars. Their pulsations and mass loss mechanisms offer clues about the processes that eventually lead to the formation of planetary nebulae, marking a crucial phase in the cosmic recycling of elements that enrich the interstellar medium and contribute to the formation of new stars and planets. Mira variables offer astronomers a fascinating window into the later stages of stellar evolution, particularly for low to intermediate mass stars. These pulsating red giant stars, named after the prototype Mira in the constellation Cetus, undergo dramatic changes in brightness over periods of about 100 to 1,000 days. By observing Mira variables, scientists can gain crucial insights into the processes that occur as stars age and expand. These stars have exhausted the hydrogen fuel in their cores and have begun fusing helium, causing them to swell to enormous sizes. Their pulsations, driven by changes in opacity and temperature in their outer layers, provide valuable data on stellar interiors and atmospheres. Studying Mira variables also sheds light on mass loss mechanisms in aging stars. As these stars pulsate, they eject significant amounts of material into space, contributing to the enrichment of the interstellar medium with heavy elements. This process is crucial for understanding the chemical evolution of galaxies and the formation of subsequent generations of stars and planets. Furthermore, Mira variables serve as important distance indicators in astronomy. Their predictable relationship between pulsation period and luminosity allows scientists to measure cosmic distances more accurately, enhancing our understanding of the scale and structure of the universe. Through continued observation and analysis of Mira variables, astronomers continue to refine models of stellar evolution and improve our knowledge of the life cycles of stars. Mira variables play a crucial role in enriching the universe with heavy elements. These pulsating red giant stars, named after the prototype star Mira, are in the late stages of stellar evolution. As they pulsate, expanding and contracting over periods of hundreds of days, they experience significant mass loss through powerful stellar winds. These stellar winds carry material from the star's outer layers into interstellar space. This ejected material is rich in carbon, nitrogen, and oxygen, elements that were produced within the star through nuclear fusion processes. Additionally, Mira variables can synthesize elements heavier than iron through a process called the slow neutron capture process, or S process. As the ejected material spreads through space, it becomes part of the interstellar medium, the vast expanses of gas and dust between stars. This enriched material can then be incorporated into new generations of stars and planets, increasing the overall abundance of heavy elements in the universe. Over time, the cumulative effect of many Mira variables shedding their outer layers contributes significantly to the chemical evolution of galaxies. This process is part of the broader cosmic recycling that gradually increases the universe's complexity and ability to form diverse structures, including the elements necessary for life as we know it. Mira variable stars, named after the prototype star Mira in the constellation Cetus, are a fascinating class of pulsating variable stars. These celestial objects are typically red giant stars nearing the end of their stellar lives. The lifespan of a Mira variable star in this pulsating phase usually ranges from a few 100,000 years to about 1 million years. During this period, Mira variables undergo dramatic changes in brightness, size, and temperature. Their luminosity can fluctuate by several magnitudes over cycles lasting anywhere from 100 to 1,000 days. This pulsation is caused by the expansion and contraction of the star's outer layers, a process driven by changes in the opacity of gases within the star. It is important to note that the Mira variable phase represents only a small fraction of the star's total lifetime, which can span billions of years. Before entering this stage, the star has already spent most of its life as a main sequence star, followed by a red giant phase. After the Mira variable stage, these stars typically expel their outer layers, forming a planetary nebula, and eventually end their lives as white dwarfs. The study of Mira variables provides valuable insights into stellar evolution, particularly the late stages of a star's life. Astronomers continue to observe and analyze these pulsating stars to better understand the complex processes that occur as stars age and approach their final transformations. Mira variables, named after the star Mira in the constellation Cetus, are a class of pulsating variable stars nearing the end of their stellar lives. These aging red giants have exhausted the hydrogen fuel in their cores and have swollen to enormous sizes, often hundreds of times larger than our Sun. As Mira variables continue to evolve, they undergo increasingly violent pulsations, shedding large amounts of their outer layers into space. This mass loss creates expanding shells of gas and dust around the star, forming what astronomers call a planetary nebula. Despite the name, these nebulae have nothing to do with planets. They were so named because early telescopes showed them as round, planet-like disks. The fate of a Mira variable depends on its initial mass. For most Mira variables, which start their lives with masses similar to our Sun, the end comes when the star has expelled most of its outer layers. The hot, dense core that remains is a white dwarf, a small, incredibly dense star about the size of Earth, but containing roughly the mass of the Sun. This white dwarf will continue to shine for billions of years as it slowly cools. However, for the most massive Mira variables, those that began their lives with several times the mass of our Sun, a different fate awaits. These stars may end their lives in a spectacular supernova explosion, briefly outshining entire galaxies before leaving behind a neutron star or even a black hole. The exact mass threshold for this fate is still a subject of ongoing research in stellar astrophysics. When a Mira variable star reaches the end of its life, it undergoes a series of dramatic changes that profoundly affect the surrounding space. These pulsating red giant stars, known for their regular variations in brightness, eventually exhaust their nuclear fuel and begin to shed their outer layers. This process creates an expanding shell of gas and dust that spreads out into the surrounding interstellar medium. As the star's outer layers are expelled, they form a planetary nebula, a glowing cloud of ionized gas that can span several light years across. This nebula enriches the surrounding space with heavy elements that were produced within the star during its lifetime. These elements, such as carbon, nitrogen, and oxygen, become the building blocks for future generations of stars and planets. The core of the Mira variable, now exposed, becomes a white dwarf star. This incredibly dense remnant, about the size of Earth but with a mass comparable to the Sun, continues to heat the expanding nebula with its intense ultraviolet radiation. Over time, the nebula dissipates, spreading its material throughout the galaxy. This cosmic recycling process plays a crucial role in the chemical evolution of the universe. The death of a Mira variable not only transforms the immediate space around it, but also contributes to the ongoing cycle of stellar birth and death that shapes our galaxy and beyond. Mira, also known as Omicron Ceti, is a fascinating star located approximately 350 light-years from Earth in the constellation Cetus. This remarkable celestial object is a binary star system consisting of a red giant star and a smaller companion star. The primary star, Mira A, is the one we typically refer to when discussing Mira's mass. Astronomers estimate that Mira A has a mass of about 1.2 times that of our Sun. This measurement is based on observations of the star's behavior, its pulsations, and its interactions with its companion. It's important to note that Mira is a variable star, meaning its brightness changes over time, which can make precise measurements challenging. The mass of Mira is particularly interesting because it represents a star in the late stages of its life. As a red giant, Mira has expanded to an enormous size, with a radius hundreds of times larger than our Sun. Despite this vast expansion, its mass remains relatively modest compared to some other giant stars in the universe. Understanding the mass of stars like Mira helps astronomers study stellar evolution and the life cycles of stars similar to our Sun. It provides valuable insights into the future fate of our own star and the processes that shape the cosmos around us. Mira, also known as Omicron Ceti, is a remarkable star that dwarfs our Sun in size. While our Sun is considered average by stellar standards, Mira is a red giant star that has swollen to enormous proportions. If we were to place Mira where our Sun is, it would extend far beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and the red planet entirely. To put this into perspective, Mira's diameter is estimated to be about 350 times that of our Sun. This means that if our Sun were the size of a golf ball, Mira would be roughly as large as a house. The sheer scale of Mira is difficult to comprehend, as it represents a stage of stellar evolution far beyond what our Sun has experienced. Mira's immense size is a result of its advanced age and the changes it has undergone as it nears the end of its life. As stars like Mira age, they expand dramatically, becoming cooler but much larger. This expansion is so significant that Mira's surface gravity is extremely low, causing it to lose mass at a rapid rate as its outer layers drift into space. Despite its enormous size, Mira is not particularly massive compared to other stars. Much of its volume is occupied by rarefied gas, making it far less dense than our Sun. This combination of immense size and relatively low mass showcases the fascinating diversity of stellar objects in our universe and the complex life cycles that stars undergo. Mira, also known as Omicron Ceti, is a fascinating variable star located about 350 light-years from Earth. As a pulsating red giant, its surface temperature fluctuates dramatically over time. At its coolest, Mira's surface temperature drops to around 2,700 degrees Celsius. This is significantly cooler than our Sun's surface, which maintains a steady temperature of about 5,500 degrees Celsius. However, Mira doesn't stay cool for long. As it pulsates, its temperature rises to a scorching 3,500 degrees Celsius. This temperature swing, occurring over a period of about 11 months, contributes to Mira's remarkable changes in brightness. At its peak, Mira can shine up to 1,000 times brighter than when it's at its dimmest. These temperature variations are linked to Mira's physical changes. As the star expands and contracts, its surface area changes, affecting both its temperature and brightness. This pulsation is driven by complex processes in the star's interior, where helium fusion occurs in a shell around the star's carbon-oxygen core. Understanding Mira's temperature fluctuations helps astronomers study the life cycles of stars and the processes that drive stellar evolution. As Mira continues its cosmic dance of expansion and contraction, it provides a spectacular show for observers and a wealth of data for scientists studying the behavior of variable stars. Mira, also known as Omicron Ceti, undergoes remarkable temperature changes during its variability cycle. This red giant star pulsates over a period of about 330 days, causing significant fluctuations in its brightness and temperature. At the coolest point in its cycle, Mira's surface temperature drops to around 2,700 Kelvin. This corresponds to the star's dimmest phase when it's barely visible to the naked eye. As the star begins to contract, it heats up dramatically. At the peak of its cycle, Mira's temperature soars to approximately 3,500 Kelvin, coinciding with its maximum brightness. These temperature swings of about 800 Kelvin are driven by the star's internal pulsations. As Mira expands and contracts, its outer layers heat and cool, causing the observed changes in temperature and brightness. This process is intrinsically linked to the star's late stage of evolution as it nears the end of its life as a red giant. The temperature variations of Mira offer astronomers valuable insights into the behavior of variable stars and the processes occurring in the final stages of stellar evolution for stars similar in mass to our Sun. Mira, also known as Omicron Ceti, is a fascinating star that has captivated astronomers for centuries. This pulsating variable star is primarily composed of hydrogen and helium, like most stars in the universe. However, its unique characteristics stem from its advanced stage of stellar evolution. As a red giant, Mira has exhausted the hydrogen in its core and is now fusing helium into carbon and oxygen. This process has led to an enrichment of these heavier elements in its outer layers. Spectroscopic observations have revealed the presence of various metals in Mira's atmosphere, including titanium, vanadium, and zirconium. One of the most intriguing aspects of Mira's composition is the presence of technetium, a radioactive element not naturally found on Earth. The detection of technetium in Mira's spectrum provides strong evidence that the star is actively producing heavy elements through nuclear fusion and mixing them to its surface through convection. Mira is also known for its strong stellar wind, which ejects material rich in carbon and oxygen into space. This process contributes to the enrichment of the interstellar medium, providing raw materials for future generations of stars and planets. The chemical composition of Mira thus offers a window into the complex life cycle of stars and the cosmic recycling of elements. Mira, a remarkable star in the constellation Cetus, stands out from its younger counterparts in several key ways. This aging red giant has undergone significant changes in its composition over its long lifetime, setting it apart from the stars we see forming today. Unlike younger stars, Mira has depleted much of its initial hydrogen fuel through nuclear fusion. As a result, its core now consists primarily of helium, with a thin shell of hydrogen fusion occurring around this helium center. This shift in elemental makeup is a hallmark of stars in their later stages of evolution. Another distinctive feature of Mira is its enriched atmosphere. Over time, the star has produced heavier elements through various nuclear processes and has transported these elements to its outer layers through convection. This has led to an abundance of carbon, oxygen, and nitrogen in its atmosphere, elements that are less prevalent in younger stars. Mira also exhibits a unique dust envelope composed of complex molecules and tiny solid particles. This dusty shroud, formed from material ejected by the star, is not typically found around younger, more stable stars. The presence of this envelope further distinguishes Mira from its youthful counterparts and provides valuable insights into the late stages of stellar evolution. At the heart of Mira, a pulsating red giant star, nuclear fusion is in a fascinating transitional phase. Unlike our Sun, which primarily fuses hydrogen into helium, Mira has exhausted its core hydrogen supply and moved on to the next stage of stellar evolution. In Mira's core, helium is now the primary fuel for nuclear fusion. The star's immense gravitational pressure and extreme temperatures have ignited helium fusion, a process known as the triple alpha process. This reaction combines 3 helium nuclei to form a single carbon nucleus, releasing energy and supporting the star against gravitational collapse. As Mira continues to evolve, it will eventually begin fusing carbon and other heavier elements in its core. This progression through different fusion stages is a hallmark of stellar evolution for stars more massive than our Sun. The energy released by these fusion reactions causes Mira to pulsate, expanding and contracting over a period of about 11 months, giving it its characteristic variable brightness. The helium fusion occurring in Mira's core not only sustains the star, but also plays a crucial role in the production of heavier elements. This process contributes to the enrichment of the interstellar medium when Mira eventually sheds its outer layers, dispersing these elements into space where they can become part of future stars and planets. Mira, also known as Omicron Ceti, is a remarkable star racing through our galaxy at an astonishing speed. This celestial speedster is hurtling through space at approximately 130 kilometers per second relative to our Sun. To put this into perspective, that is over 460,000 kilometers per hour. This rapid motion is not unusual for stars, but Mira's speed is certainly on the higher end of the spectrum. As it travels, Mira leaves behind a spectacular tail of stellar material, stretching an incredible 13 light-years in length. This cosmic wake, visible only in ultraviolet light, is a testament to the star's swift journey through the Milky Way. Mira's high velocity is likely the result of gravitational interactions with other stars, or possibly due to the explosive events in its past. As a variable star, Mira's brightness changes dramatically over time, adding another layer of intrigue to this celestial traveler. The star's rapid movement through space serves as a reminder of the dynamic nature of our galaxy, where even seemingly fixed points of light are in constant motion, participating in a grand cosmic dance that unfolds over millions of years. Mira, also known as Omicron Ceti, is a fascinating variable star located approximately 330 light-years from Earth in the constellation Cetus. This red giant star has captivated astronomers for centuries due to its dramatic changes in brightness. However, when it comes to Mira's rotational period, scientists have faced challenges in determining an exact value. The difficulty in measuring Mira's rotation stems from its nature as a pulsating variable star. These pulsations, which cause the star to expand and contract, can mask or interfere with the signals that would typically indicate rotation. Additionally, Mira's status as an aging star in the late stages of its life complicates matters further, as its outer layers are less stable than those of younger stars. Despite these challenges, some studies have suggested that Mira's rotational period might be on the order of several hundred days. However, this estimate comes with significant uncertainty, and more research is needed to confirm and refine this value. The complex interplay between Mira's pulsations, its binary companion, and its evolving structure makes precise measurements of its rotation a continuing area of astronomical investigation. Understanding Mira's rotation could provide valuable insights into the behavior of variable stars and the late stages of stellar evolution. As technology advances and our observational techniques improve, astronomers hope to unlock more secrets about this enigmatic star and its intriguing properties. Mira, the pulsating variable star in the constellation Cetus, possesses a magnetic field that sets it apart from many other stars. Unlike the steady magnetic fields observed in stars like our Sun, Mira's magnetic field is dynamic and complex, changing in strength and structure as the star pulsates. The magnetic field of Mira is considerably stronger than that of our Sun, with some measurements suggesting it could be up to 100 times more powerful. This intense magnetism plays a crucial role in shaping Mira's stellar wind and the material it ejects into space. The field's strength and configuration vary as the star expands and contracts during its pulsation cycle, which occurs over a period of about 330 days. Compared to other variable stars, Mira's magnetic field is particularly noteworthy. While many variable stars exhibit some magnetic activity, the combination of Mira's strong field and its pulsating nature creates unique phenomena. For instance, the magnetic field interacts with the stellar wind to create complex structures in the surrounding space, including arcs, loops, and filaments of ejected material. The study of Mira's magnetic field provides valuable insights into the late stages of stellar evolution. As Mira is a red giant star nearing the end of its life, its magnetic behavior offers clues about the processes that occur in aging stars and how they influence the surrounding interstellar medium. This makes Mira an important target for astronomers seeking to understand stellar magnetism and its effects on the cosmic environment. Mira, also known as Omicron Ceti, is currently in the asymptotic giant branch stage of stellar evolution. This phase occurs towards the end of a star's life, after it has exhausted the hydrogen fuel in its core and moved off the main sequence. Mira began as a star similar in mass to our Sun, but has now swollen to become a red giant with a diameter roughly 400 times larger than the Sun. During this stage, Mira alternates between burning hydrogen and helium in shells surrounding its carbon and oxygen core. This process causes the star to pulsate, dramatically changing in brightness over a period of about 11 months. At its brightest, Mira can be visible to the naked eye, while at its dimmest, it requires a telescope to observe. As an asymptotic giant branch star, Mira is also shedding its outer layers into space, creating a stellar wind that enriches the interstellar medium with heavy elements. This material forms an extended envelope around the star, which astronomers have observed stretching far into space. Mira's current evolutionary stage is relatively short-lived on cosmic timescales. In the future, it will eventually expel most of its outer layers, forming a planetary nebula with a white dwarf at its center. This fate awaits many stars of similar mass, including our own Sun, billions of years from now. Mira, also known as Omicron Ceti, is a fascinating star that has captured the attention of astronomers for centuries. This pulsating variable star is estimated to be approximately 6 billion years old. To put this into perspective, Mira is older than our own Sun, which is about 4.5 billion years old. Mira's advanced age places it in a late stage of stellar evolution. It has already exhausted the hydrogen fuel in its core and has expanded to become a red giant star. This expansion is a natural part of a star's life cycle as it ages, and Mira has swollen to an enormous size, with a diameter roughly 400 times that of our Sun. The age of Mira has been determined through careful study of its composition, brightness variations, and other observable characteristics. Astronomers use sophisticated models of stellar evolution to estimate the ages of stars based on these factors. However, it is important to note that age estimates for individual stars can have some uncertainty. Mira's age and its current evolutionary state make it an invaluable subject for studying the life cycles of stars similar to our Sun. By observing Mira, scientists can gain insights into the potential future of our own star billions of years from now. When Mira was a young star, it was vastly different from the pulsating red giant we observe today. Billions of years ago, Mira began its life as a main sequence star, much like our Sun. It was smaller, hotter, and more stable than its current form. During this youthful phase, Mira steadily fused hydrogen into helium in its core, releasing energy that maintained its structure and brightness. As a young star, Mira would have appeared bluish-white, with a surface temperature several thousand degrees hotter than it is now. Its size was likely similar to or slightly larger than our Sun, rather than the enormous proportions it has reached in its current stage. The star would have rotated faster in its youth, as it had not yet expanded to its current size. Mira's early life was characterized by relative constancy. Unlike its current behavior of dramatic brightness fluctuations, young Mira maintained a steady luminosity. It would have been surrounded by a protoplanetary disk from which planets might have formed, though we have no evidence of existing planets around Mira today. This stable period of Mira's life lasted for billions of years before it began to exhaust its core hydrogen fuel. As Mira aged, it started the transition toward its current state, expanding and cooling as it evolved off the main sequence and eventually becoming the remarkable variable star we study today. Mira, also known as Omicron Ceti, has undergone significant changes throughout its stellar lifetime. This pulsating variable star began as a main sequence star, much like our Sun, fusing hydrogen in its core. Over billions of years, it exhausted its central hydrogen supply and evolved into a red giant. As a red giant, Mira swelled to enormous proportions, with a diameter roughly 400 times that of our Sun. Its outer layers became cooler and less dense, causing the star to pulsate. These pulsations result in dramatic changes in Mira's brightness, varying by up to 1,000 times over a period of about 330 days. Mira is now in the asymptotic giant branch phase of its life, characterized by alternating periods of hydrogen and helium shell burning. This stage is marked by significant mass loss, with Mira shedding its outer layers into space at a rate of about 1 Earth mass every 7 years. This process has created a vast tail of ejected material stretching over 13 light-years behind the star. In its future, Mira will continue to lose mass until its outer layers are completely ejected, forming a planetary nebula. The remaining core will become a white dwarf, marking the final stage in the life of this remarkable star. Mira serves as a preview of the fate that awaits our own Sun billions of years from now. Mira, also known as Omicron Ceti, is a fascinating star that offers us a glimpse into the future stages of stellar evolution. As a pulsating variable star, Mira is currently in the red giant phase of its life cycle. However, its journey is far from over. The next significant stage in Mira's evolution will be the shedding of its outer layers. As Mira continues to burn through its remaining fuel, it will become increasingly unstable. This instability will cause the star to expel large portions of its mass into space, creating a spectacular display known as a planetary nebula. During this process, Mira's core will become exposed, transforming into a hot, dense, stellar remnant called a white dwarf. This white dwarf will be incredibly small compared to Mira's current size, yet it will retain a significant portion of the star's original mass. The planetary nebula phase is relatively brief in astronomical terms, lasting only a few tens of thousands of years. After this, the white dwarf will slowly cool over billions of years, eventually fading into a cold, dark, stellar corpse. This fate awaits not only Mira, but also our own Sun in the distant future, offering us a preview of the cosmic cycle of stellar life and death. Mira, also known as Omicron Ceti, is a fascinating variable star that has captivated astronomers for centuries. This pulsating red giant star is currently in a phase of its life cycle where it expands and contracts, causing dramatic changes in its brightness over time. Based on current stellar evolution models, astronomers estimate that Mira will remain in its present pulsating phase for approximately 100,000 to 1 million years. This relatively short time span in cosmic terms represents a crucial stage in the star's life, during which it sheds its outer layers and prepares for its eventual transformation into a white dwarf. During this phase, Mira will continue its characteristic cycle of brightening and dimming every 332 days, giving observers on Earth a celestial light show that repeats roughly once per year. This predictable variability has made Mira a valuable target for both professional and amateur astronomers, allowing them to study the processes of stellar evolution in real time. As Mira progresses through this stage, it will gradually lose more of its mass through stellar winds, enriching the surrounding interstellar medium with heavy elements. This material may eventually contribute to the formation of new stars and planets, showcasing the cyclical nature of stellar life and death in our universe. Mira, a red giant star in the constellation Cetus, faces an intriguing fate as it approaches the end of its life. This pulsating variable star, also known as Omicron Ceti, will undergo significant changes in its final stages. As Mira exhausts its nuclear fuel, it will begin to shed its outer layers, creating a beautiful planetary nebula. This glowing shell of gas and dust will expand outward, illuminated by the hot, exposed core of the dying star. The nebula will take on intricate shapes and vibrant colors, offering a spectacular celestial display for future observers. At the heart of this nebula, Mira's core will contract and heat up, becoming a white dwarf. This small, dense stellar remnant, about the size of Earth but with a mass close to that of the Sun, will continue to shine for billions of years as it slowly cools. The white dwarf will be composed primarily of carbon and oxygen, the products of helium fusion during Mira's red giant phase. The fate of Mira serves as a preview of our own Sun's distant future, offering astronomers valuable insights into stellar evolution and the life cycles of medium-sized stars throughout the universe. Mira, also known as Omicron Ceti, is a fascinating star that offers us a glimpse into the potential future of our own Sun. Unlike our relatively stable yellow dwarf, Mira is a red giant star nearing the end of its life cycle. This celestial body has swollen to enormous proportions, with a diameter roughly 400 times that of our Sun. The evolution of Mira diverges significantly from our Sun's current state. While our star steadily fuses hydrogen in its core, Mira has exhausted its central hydrogen supply and now burns helium. This shift in fuel source has led to dramatic changes in Mira's structure and behavior. Perhaps most notably, Mira pulsates, varying in brightness over a period of about 11 months. During this cycle, it can become bright enough to see with the naked eye before fading from view entirely. Another striking difference is Mira's mass loss. As it pulsates, Mira sheds its outer layers into space, creating a tail of ejected material stretching an astonishing 13 light-years behind it. This process gradually strips away the star's mass, a fate our Sun will likely share in the distant future. Studying Mira provides astronomers with valuable insights into stellar evolution. By observing this star, we can better understand the processes that will shape our Sun's future roughly 5 billion years from now, when it too will swell into a red giant, dramatically altering our solar system. Mira, a remarkable red giant star, offers us a glimpse into the potential future of our Sun and solar system. Located about 350 light-years from Earth, Mira is a binary star system consisting of an aging red giant and a smaller companion star. As our Sun ages, it will eventually expand into a red giant, much like Mira has done. Mira's most striking feature is its colossal tail, stretching an astonishing 13 light-years across space. This tail is formed as Mira sheds its outer layers, leaving behind a trail of carbon, oxygen, and other elements. This process of stellar mass loss provides crucial insights into how our own solar system might evolve when the Sun reaches a similar stage in its life cycle. The fate of Mira also hints at the eventual transformation of our Sun into a white dwarf. As Mira continues to lose mass, its core will be exposed, forming a small, dense, stellar remnant. This process will likely occur in our solar system billions of years from now, dramatically altering the environment of our planets. Studying Mira allows astronomers to better understand the later stages of stellar evolution and the impact on surrounding planets. While the Earth will likely be engulfed when our Sun expands, the outer planets may experience conditions similar to those in the Mira system, offering a preview of our solar system's distant future. Astronomers use a combination of observational data and theoretical models to predict the future stages of Mira's evolution. By studying Mira's current characteristics, including its mass, temperature, and chemical composition, scientists can compare these properties to well-established stellar evolution models. These models, developed through decades of astronomical research and computer simulations, provide a roadmap for how stars of different masses progress through their life cycles. For a star like Mira, which is already in its red giant phase, astronomers can project its future based on its current state and our understanding of stellar physics. One key factor in predicting Mira's fate is its pulsating nature. As a variable star, Mira's brightness fluctuates over a period of about 11 months, indicating complex processes occurring within its structure. By analyzing these pulsations and how they change over time, astronomers can gain insights into the star's internal dynamics and how they might evolve. Additionally, spectroscopic observations reveal the chemical elements present in Mira's atmosphere, providing clues about its age and the nuclear fusion processes occurring in its core. This information, combined with measurements of Mira's mass loss rate, allows scientists to estimate how long it will remain in its current phase and what transformations it may undergo in the future, such as becoming a planetary nebula with a white dwarf at its center. Mira, also known as Omicron Ceti, is a remarkable star that undergoes astonishing changes in brightness. This celestial wonder is a long-period variable star, pulsating over a cycle of about 330 days. During this time, Mira's brightness can increase by a factor of around 1,000, making it visible to the naked eye before fading back to near invisibility. The primary cause of these dramatic fluctuations lies in Mira's nature as a red giant star nearing the end of its life. As Mira burns through its fuel, it expands and contracts in a rhythmic pattern. When the star expands, its outer layers cool and become more opaque, causing it to dim. As it contracts, the star heats up, becoming more transparent and thus brighter. This pulsation is driven by changes in the ionization state of helium in the star's atmosphere. As helium becomes ionized, it traps more of the star's internal energy, causing expansion. When the helium recombines with electrons, the trapped energy is released, leading to contraction. This cycle repeats, creating the characteristic brightness variations. Adding to this spectacle, Mira is shedding its outer layers, creating a surrounding shell of gas and dust. This material can further affect the star's apparent brightness, sometimes amplifying or muting the pulsation effects. The interplay between Mira's internal pulsations and its evolving stellar environment creates a cosmic light show that continues to captivate astronomers and stargazers alike. Mira, also known as Omicron Ceti, is a remarkable variable star that undergoes dramatic changes in brightness. During its cycle, Mira's luminosity fluctuates by an astonishing factor of about 1,000. This means that at its brightest, Mira can outshine its dimmest state by roughly 10 magnitudes on the astronomical scale. At its peak, Mira can reach a magnitude of about 3, making it easily visible to the naked eye in dark skies. However, when it fades to its minimum brightness, it dims to around magnitude 9 or 10, becoming so faint that it requires a telescope to be seen. This extreme variation occurs over a period of approximately 11 months, creating a fascinating celestial spectacle for astronomers and stargazers alike. The cause of these dramatic brightness changes lies in the nature of Mira itself. It is a pulsating variable star in the late stages of its life, expanding and contracting rhythmically. As it pulsates, its surface temperature and size change, leading to the observed fluctuations in brightness. This pulsation is driven by complex processes in the star's interior, involving the interplay of gravity, pressure, and energy transfer. Mira's remarkable variability makes it a valuable target for astronomical study. By observing its brightness changes over time, scientists can gain insights into the life cycles of stars and the physical processes that drive stellar evolution. The star's extreme range of brightness also serves as a powerful reminder of the dynamic and ever-changing nature of the universe. Mira, also known as Omicron Ceti, is a fascinating variable star that captivates astronomers with its rhythmic changes in brightness. This pulsating red giant star completes its variability cycle over a period of approximately 332 days. During this cycle, Mira's brightness fluctuates dramatically, ranging from being barely visible to the naked eye at its dimmest to becoming one of the brightest stars in its constellation at its peak. This lengthy cycle sets Mira apart from many other variable stars, which often have much shorter periods of variability. The star's name, which means wonderful or astonishing in Latin, is a testament to its remarkable behavior. Mira's extended period of variability allows astronomers to study its changes over time, providing valuable insights into the late stages of stellar evolution. Mira's variability is caused by pulsations in its outer layers, which expand and contract, altering the star's size and temperature. These pulsations are driven by complex interactions between gravity, pressure, and the opacity of the star's atmosphere. As Mira expands and cools, it becomes dimmer, and as it contracts and heats up, it brightens, creating the cyclical pattern we observe from Earth. Mira, also known as Omicron Ceti, is a fascinating variable star that captivates astronomers with its rhythmic changes in brightness. This red giant star follows a remarkably consistent pattern of brightening and dimming, completing its cycle approximately every 332 days. This predictable variability has made Mira a valuable celestial timekeeper for astronomers throughout history. The regularity of Mira's cycle is so reliable that it has become the prototype for an entire class of variable stars known as Mira variables. These stars are characterized by their long-period pulsations and significant changes in luminosity. In the case of Mira itself, the brightness can vary by up to 1,000 times between its dimmest and brightest states. Despite its overall consistency, Mira's cycle does exhibit some subtle variations. Careful observations have revealed that the exact period can fluctuate slightly, typically by a few days. These minor deviations are thought to be caused by complex interactions within the star's atmosphere and internal structure. Astronomers continue to study Mira and its namesake class of variables, using advanced telescopes and modeling techniques to unravel the intricacies of their pulsation mechanisms. This ongoing research not only deepens our understanding of stellar evolution, but also provides valuable insights into the later stages of a star's life, offering a glimpse into the potential future of our own sun. Mira, also known as Omicron Ceti, undergoes remarkable changes in size as it cycles through its brightness variations. This pulsating variable star expands and contracts dramatically over a period of about 332 days. At its dimmest, Mira shrinks to roughly 400 times the size of our Sun. However, as it brightens, the star swells to an enormous size, reaching up to 700 times the Sun's diameter. This expansion is so vast that if Mira were placed at the center of our solar system, it would extend beyond the orbit of Mars. These size fluctuations are intrinsically linked to Mira's changes in brightness. As the star expands, its outer layers cool and become less luminous, causing it to dim. When it contracts, the star heats up and shines more brightly. This pulsation is driven by changes in the opacity of the star's outer layers, creating a cyclical pattern of expansion and contraction. The extreme size variations of Mira offer astronomers a unique opportunity to study the late stages of stellar evolution. As a red giant nearing the end of its life, Mira provides valuable insights into the future fate of our own Sun and similar stars throughout the universe. Mira, also known as Omicron Ceti, is a remarkable star that significantly impacts its cosmic neighborhood. This red giant star pulsates dramatically, changing in brightness over a period of about 330 days. During its brightest phases, Mira can be visible to the naked eye, while at its dimmest, it requires a telescope to observe. This variability has profound effects on Mira's surroundings. As the star expands and contracts, it ejects vast amounts of material into space. This process creates a stellar wind that is much more intense than that of our Sun. In fact, Mira sheds enough mass to equal that of Earth every 10 years. The ejected material forms a long, comet-like tail, stretching an astonishing 13 light-years behind the star as it moves through space. This tail contains complex molecules and elements that enrich the interstellar medium. These materials can eventually become part of new stars and planets, making Mira a vital contributor to the cosmic recycling process. Moreover, the pulsations of Mira create shock waves that propagate through its extended atmosphere. These waves heat the gas around the star, causing it to glow and creating complex structures visible in ultraviolet light. This dynamic environment serves as a natural laboratory for studying stellar evolution and the life cycles of stars, similar to what our Sun will become in the distant future. Mira, also known as Omicron Ceti, offers astronomers a wealth of knowledge about the late stages of stellar evolution. This pulsating variable star expands and contracts over a period of about 330 days, dramatically changing in brightness as it does so. By studying these variations, scientists can gain insights into the internal structure and dynamics of aging stars. The variability of Mira provides a window into the processes of mass loss in red giant stars. As Mira pulsates, it sheds its outer layers into space, creating a surrounding envelope of gas and dust. This material eventually enriches the interstellar medium, contributing to the formation of new stars and planets. Observing this process in real time allows researchers to better understand how elements are dispersed throughout the galaxy. Furthermore, Mira's changes in brightness and size offer clues about the final stages of stellar life for stars similar to our Sun. By measuring the star's temperature, luminosity, and composition at different points in its cycle, astronomers can refine models of stellar evolution and improve predictions about the future of our own star. Studying Mira's variability also aids in the calibration of cosmic distance measurements. As a type of star with well-understood properties, Mira variables serve as important cosmic yardsticks, helping astronomers gauge distances to other stars and galaxies. This contributes to our overall understanding of the universe's scale and structure. Astronomers employ a variety of techniques to measure and track the variability of Mira, a pulsating variable star in the constellation Cetus. Visual observations play a crucial role in this process. Amateur and professional astronomers regularly monitor Mira's brightness changes using their eyes or small telescopes, comparing its luminosity to nearby stars of known magnitude. These observations, collected over time, help create a light curve that shows how Mira's brightness fluctuates over its roughly 11-month cycle. More precise measurements are obtained through photometry, a technique that uses specialized instruments to accurately measure the amount of light received from the star. Astronomers use photometers attached to telescopes to capture Mira's light at different wavelengths, providing detailed information about its changing brightness and temperature. This method allows for the detection of subtle variations that might be missed by visual observations alone. Spectroscopy also plays a vital role in studying Mira's variability. By analyzing the star's spectrum, astronomers can track changes in its temperature, size, and chemical composition throughout its pulsation cycle. These spectral observations reveal how Mira's outer layers expand and contract, causing variations in its brightness and color. Long-term monitoring programs, both ground-based and space-based, have been instrumental in understanding Mira's behavior. Observatories around the world collaborate to ensure continuous coverage of the star's variability, while space telescopes provide uninterrupted observations free from atmospheric interference. This wealth of data allows astronomers to refine models of Mira's pulsations and better understand the physical processes driving its remarkable variability. Mira is not alone in its fascinating variability. Many other stars in our galaxy and beyond display similar pulsating behavior, though each with its own unique characteristics. These stars belong to a class known as long-period variables, with Mira itself being the prototype of a subgroup called Mira variables. One notable example is Chi Cygni, located in the constellation Cygnus. This star undergoes dramatic changes in brightness over a period of about 408 days, rivaling Mira in its impressive range of variability. At its brightest, Chi Cygni can be visible to the naked eye, while at its dimmest, it requires a telescope to observe. Another intriguing Mira-type variable is R Leonis in the constellation Leo. This star pulsates over a period of about 312 days, changing its brightness by a factor of nearly 2,500. R Leonis is particularly interesting because it is one of the reddest stars visible from Earth, appearing almost blood red when viewed through a telescope. These pulsating stars are typically red giants nearing the end of their lives. As they exhaust their fuel, they become unstable, expanding and contracting in a cosmic dance that we observe as changes in brightness. This variability provides astronomers with valuable insights into stellar evolution and the life cycles of stars similar to our Sun. Our understanding of Mira's variability has undergone significant changes since its discovery in the late 16th century. Initially observed by David Fabricius, Mira was thought to be a new star that appeared and disappeared. This led to its name, which means wonderful or astonishing in Latin. As astronomers continued to observe Mira over the centuries, they realized it wasn't a new star at all, but rather a variable star with a regular cycle of brightening and dimming. By the 19th century, scientists had determined that Mira's brightness fluctuates over a period of about 11 months, making it the prototype for a class of long-period variable stars now known as Mira variables. Modern astrophysics has revealed that Mira's variability is caused by pulsations in its outer layers. These pulsations are driven by changes in the opacity of ionized helium in the star's atmosphere. As Mira expands and contracts, its brightness can change by up to 1,000 times, making it visible to the naked eye at its peak before fading to invisibility. Recent observations using advanced telescopes and space-based instruments have uncovered even more intriguing details about Mira. We now know it's part of a binary system with a white dwarf companion, and it's shedding its outer layers, creating a tail of debris as it moves through space. This ongoing research continues to deepen our understanding of stellar evolution and the complex processes that drive stellar variability. Mira, also known as Omicron Ceti, is indeed part of a binary star system. This famous variable star, whose brightness fluctuates dramatically over a period of about 330 days, has a smaller companion orbiting it. The companion star, designated as Mira B or VZ Ceti, was discovered in 1923 by Robert Grant Aitken. Mira B is a fascinating object in its own right. It is believed to be a white dwarf, the remnant core of a star that has exhausted its nuclear fuel. This compact stellar corpse orbits the much larger and more luminous Mira A at a distance of roughly 70 astronomical units, taking approximately 500 years to complete one orbit. The relationship between Mira and its companion is complex and intriguing. As Mira pulsates and expands, it sheds material into space. Some of this material is captured by the gravitational pull of Mira B, forming an accretion disk around the white dwarf. This interaction between the two stars creates a unique astrophysical laboratory, allowing scientists to study various phenomena such as mass transfer in binary systems and the evolution of stars in close proximity. The Mira system serves as an excellent example of the diversity and complexity of stellar arrangements in our galaxy. It reminds us that many stars we see as single points of light in the night sky are actually intricate systems with their own cosmic dances and evolutionary stories. Mira's companion is a fascinating stellar object known as a white dwarf star. These compact remnants are formed when stars like our Sun exhaust their nuclear fuel and shed their outer layers. White dwarfs are incredibly dense, packing roughly the mass of the Sun into a volume about the size of Earth. The white dwarf orbiting Mira is part of a binary system, circling the larger, pulsating red giant star every 500 years. This cosmic dance between the two stars creates a unique environment where material from Mira's expanding atmosphere is sometimes captured by the white dwarf's intense gravity. Despite its small size, the white dwarf exerts a significant influence on its larger companion. The interaction between these two very different stars provides astronomers with valuable insights into stellar evolution, mass transfer processes, and the complex dynamics of binary star systems. The presence of this white dwarf companion adds another layer of intrigue to the already captivating Mira system, making it a prime target for ongoing astronomical research and observation. Mira, also known as Omicron Ceti, has long been recognized as a variable star, but the discovery of its companion was a more recent development in astronomical history. The companion to Mira was first detected in 1995 using the Hubble Space Telescope's Faint Object Camera. This groundbreaking observation revealed a small, hot object orbiting the much larger and cooler Mira. The discovery came as a surprise to astronomers who had been studying Mira for centuries without realizing it was part of a binary system. The companion, now known as Mira B, is believed to be a white dwarf star, the dense remnant core of a star that has exhausted its nuclear fuel. What made this discovery particularly challenging was the vast difference in brightness between Mira and its companion. Mira itself is a red giant star that varies dramatically in brightness over a period of about 11 months. Its companion, being much smaller and fainter, was easily lost in Mira's glare, requiring the advanced capabilities of the Hubble Space Telescope to detect it. This finding not only expanded our understanding of Mira, but also provided valuable insights into the evolution of binary star systems and the complex interactions that can occur between stars at different stages of their lives. The Mira system continues to be a subject of intense study, offering astronomers a unique laboratory for investigating stellar evolution and binary star dynamics. Mira and its companion star, known as Mira B, orbit each other in a fascinating celestial dance. These two stars are separated by an average distance of about 60 astronomical units. To put this in perspective, 1 astronomical unit is the distance between Earth and the Sun, roughly 93 million miles. This means that Mira and its companion are typically about 5,580,000,000 miles apart. However, their orbit is not perfectly circular. The distance between Mira and its companion varies as they move through their orbital cycle, which takes approximately 500 years to complete. At their closest approach, called periastron, they can come as near as 40 astronomical units to each other. At their farthest point, known as apastron, they can be separated by up to 100 astronomical units. This variable separation has significant implications for the interaction between the two stars. Mira, a red giant, is losing mass through stellar winds, and some of this material is captured by its smaller, hotter companion. The changing distance between the stars affects the rate and dynamics of this mass transfer, creating a complex and ever-evolving stellar relationship. Mira and its companion star form a fascinating binary system that showcases the complex interplay between celestial bodies. Mira, also known as Omicron Ceti, is a red giant star nearing the end of its life. Its companion is a smaller, hotter star, believed to be a white dwarf. The two stars orbit each other in an elliptical path, completing one revolution approximately every 500 years. As they dance through space, Mira sheds its outer layers, creating a wind of gas and dust that flows outward. Some of this material gets captured by the gravitational pull of the companion star, forming an accretion disk around it. This transfer of matter between the stars leads to periodic outbursts of energy and light. The white dwarf companion occasionally experiences sudden increases in brightness as it consumes the accumulated material from Mira. These events, known as dwarf nova outbursts, can cause the overall brightness of the system to fluctuate dramatically. The interaction between Mira and its companion offers astronomers a unique opportunity to study stellar evolution, mass transfer, and the life cycles of binary star systems. As Mira continues to lose mass, it will eventually become a white dwarf itself, while its companion may undergo further changes, potentially leading to more energetic events in the distant future. Mira, a remarkable star system, showcases the intricate dance of stellar evolution influenced by binary interactions. The primary star, Mira A, is a pulsating red giant that undergoes regular changes in brightness. Its companion, Mira B, plays a crucial role in shaping the system's dynamics and the fate of Mira A. The presence of Mira B significantly affects the mass loss process of Mira A. As Mira A expands during its red giant phase, it sheds its outer layers. Some of this material is captured by the gravitational pull of Mira B, forming an accretion disk around the smaller star. This interaction accelerates the mass loss rate of Mira A, causing it to evolve more rapidly than it would if it were a solitary star. The companion's influence extends beyond mass transfer. The gravitational interplay between the two stars distorts Mira A's shape and alters its pulsation patterns. These changes affect the star's internal structure and energy distribution, potentially impacting its lifespan and eventual fate. Furthermore, the binary nature of the system creates complex patterns in the surrounding space. As Mira A loses mass, the material forms a spiral structure due to the orbital motion of the two stars. This intricate distribution of stellar material provides valuable insights into the processes of mass loss and binary star evolution, making Mira a captivating subject for astronomers studying the life cycles of stars. Mira, the famous pulsating variable star, has a fascinating relationship with its companion star that influences its variability. This binary system consists of Mira A, a red giant, and Mira B, a smaller white dwarf. The interaction between these two stars plays a crucial role in shaping Mira's distinctive brightness fluctuations. The gravitational pull of Mira B affects the outer layers of Mira A, causing distortions and irregularities in its pulsations. As Mira A expands and contracts, the companion's influence becomes more pronounced, leading to slight variations in the timing and magnitude of Mira's brightness changes. This interplay results in a complex dance of stellar material, with Mira B accreting some of the mass lost by Mira A during its pulsation cycles. Furthermore, the companion's presence alters the distribution of gas and dust around Mira A. This redistribution of material can affect how light from Mira A is absorbed and scattered, contributing to the observed variations in brightness. The orbital motion of the two stars also introduces periodic perturbations in Mira's variability pattern, adding another layer of complexity to its light curve. These interactions between Mira and its companion demonstrate the intricate nature of binary star systems and their impact on stellar variability. By studying this celestial pair, astronomers gain valuable insights into the dynamics of evolved stars and the processes that shape their long-term evolution. Mira, also known as Omicron Ceti, is a fascinating binary star system located approximately 300 light-years from Earth. This system consists of a red giant star, Mira A, and its smaller companion, Mira B. The two stars orbit each other in a cosmic dance that takes centuries to complete. The orbital period of Mira and its companion is remarkably long, spanning approximately 490 years. This means that if you were to observe Mira at the start of its orbit, you would need to wait nearly 5 centuries to see it return to the same relative position. This extended timeframe presents a unique challenge for astronomers studying the system, as it requires observations spanning multiple human lifetimes to fully understand its orbital dynamics. The vast separation between Mira A and Mira B contributes to this lengthy orbital period. On average, the two stars are about 100 astronomical units apart. To put this into perspective, 1 astronomical unit is the distance between Earth and the Sun. This means that the distance between Mira and its companion is roughly 100 times the distance between our planet and its star. Despite the challenges posed by such a long orbital period, astronomers have made significant progress in understanding the Mira system. Advanced telescopes and long-term observational data have allowed scientists to piece together the complex relationship between these two stars, shedding light on the dynamics of binary systems and the evolution of stars in the later stages of their lives. The Mira binary system stands out as a fascinating example among the many binary star systems in our galaxy. At its heart lies Mira A, a pulsating variable star that brightens and dims dramatically over a period of about 330 days. This rhythmic change in luminosity is so pronounced that Mira A can sometimes be seen with the naked eye, while at other times it fades from view entirely. What makes the Mira system particularly intriguing is its companion, Mira B. Unlike many binary pairs where both stars are of similar size and type, Mira B is a much smaller, hotter star known as a white dwarf. This creates a unique dynamic within the system, as Mira B orbits through the outer layers of the much larger Mira A, accreting material from its companion. This interaction between the two stars leads to some remarkable phenomena. As Mira A sheds its outer layers through stellar winds, some of this material is captured by Mira B, forming an accretion disk around the smaller star. This process can cause periodic flares and outbursts, adding another layer of variability to the system. Compared to more typical binary systems, where stars might simply orbit each other at a distance, the Mira system offers astronomers a rare opportunity to study complex stellar interactions up close. Its unique characteristics make it an invaluable target for research into stellar evolution, mass transfer between stars, and the life cycles of both red giants and white dwarfs. Mira and its companion star offer a fascinating glimpse into the complex world of binary star evolution. This system, located about 400 light-years from Earth, consists of Mira A, a red giant star, and Mira B, a smaller companion that is likely a white dwarf. Their interaction provides valuable insights into how binary stars influence each other over time. One key lesson from the Mira system is the process of mass transfer between stars. As Mira A expands in its red giant phase, it sheds material into space. Some of this material is captured by the gravitational pull of Mira B, forming an accretion disk around the smaller star. This transfer of mass demonstrates how binary stars can significantly alter each other's composition and evolution. The Mira system also sheds light on the phenomenon of stellar wind. Mira A is known for its strong stellar wind, which creates a tail of material stretching for an astonishing 13 light-years behind the star. This wind is partly shaped by the gravitational influence of Mira B, illustrating how companion stars can affect the distribution of material in space around evolved stars. Furthermore, studying Mira and its companion helps astronomers understand the later stages of stellar evolution in binary systems. As Mira A continues to evolve, it may eventually become a white dwarf like its companion, offering a preview of the potential fate of many binary star systems in our galaxy. This knowledge is crucial for developing more accurate models of stellar evolution and improving our understanding of the life cycles of stars in the universe. Mira, a remarkable star in our galaxy, is leaving behind an extraordinary trail that stretches across the cosmos. This cosmic wake extends an astonishing 30 light-years in length, making it visible even from Earth. The trail consists of carbon, oxygen, and other elements that Mira sheds as it hurtles through space at incredible speeds. Unlike most stars that appear stationary to us, Mira is moving rapidly through the galaxy, traveling at about 300,000 miles per hour. As it races through space, it encounters the thin gas and dust that exist between stars. This interstellar medium acts like a cosmic wind, pushing against the material Mira ejects and shaping it into a distinctive tail. The material in Mira's tail is actually the star's outer layers, which are being stripped away as it ages. Mira is a red giant star nearing the end of its life, and it's losing mass at a prodigious rate. Every year, Mira sheds enough material to make an Earth-sized planet. This ejected matter forms the spectacular trail we observe. What makes Mira's tail particularly fascinating is its turbulent nature. The trail twists and turns, forming eddies and swirls that resemble the wake left by a ship moving through water. These complex structures in the tail provide astronomers with valuable information about the dynamics of stellar winds and the interactions between stars and the interstellar medium. Mira, a remarkable star in our galaxy, leaves behind an astonishing trail as it hurtles through space. This cosmic wake stretches an incredible 13 light-years in length. To put this into perspective, if we were to measure this distance in kilometers, it would extend for about 123 trillion kilometers. This enormous trail is composed of material that Mira sheds as it moves, creating a path that dwarfs many other celestial phenomena in our cosmic neighborhood. The sheer scale of Mira's trail becomes even more impressive when we consider that it spans roughly 20,000 times the distance from our Sun to Pluto. This colossal streak across the cosmos was only discovered in 2007 thanks to observations made by the Galaxy Evolution Explorer space telescope. The revelation of this stellar tail has provided astronomers with valuable insights into the life cycles of stars and the ways in which they influence the space around them. Mira's trail is not just remarkable for its size, but also for what it tells us about stellar evolution. As Mira races through space at about 130 kilometers per second, it leaves behind carbon, oxygen, and other elements. This material enriches the interstellar medium, potentially becoming the building blocks for future stars and planets. Mira's journey through the cosmos is helping to sow the seeds for new celestial bodies, showcasing the interconnected nature of our universe. The trail we observe in the night sky is actually the tail of a comet. This remarkable celestial phenomenon is composed of two distinct parts, a dust tail and an ion tail. The dust tail consists of tiny particles of rock and ice that are released from the comet's nucleus as it approaches the Sun. These particles reflect sunlight, creating a bright, curved path that can stretch for millions of kilometers behind the comet. The ion tail, on the other hand, is made up of ionized gases that are pushed away from the comet by the solar wind. This tail appears as a straight, bluish streak extending directly away from the Sun. As the comet moves closer to our star, the heat causes its icy surface to sublimate, turning directly from solid to gas. This process releases trapped dust and debris, which forms the visible trail we see from Earth. The size and brightness of a comet's tail can vary greatly depending on its composition and its proximity to the Sun. Some comet tails can span tens of millions of kilometers in length, creating a spectacular sight for observers on Earth. Mira's trail, a remarkable celestial phenomenon, was discovered through the keen observations of astronomers using the Galaxy Evolution Explorer space telescope, also known as GALEX. This ultraviolet space telescope, launched by NASA in 2003, was designed to study the history of star formation in the universe. In 2007, astronomers were analyzing data from GALEX when they noticed something extraordinary. They observed a long, narrow streak of ultraviolet light trailing behind the star Mira, also called Omicron Ceti. This streak extended an astonishing 13 light-years in length, making it visible even to the naked eye if human eyes could detect ultraviolet light. The discovery of Mira's trail was unexpected and exciting for astronomers. It revealed that Mira, a red giant star nearing the end of its life, was shedding material as it moved through space at high speed. This material, consisting of carbon, oxygen, and other elements, forms a wake behind the star, much like the wake left by a boat moving through water. This finding not only provided new insights into the life cycle of stars, but also demonstrated how dying stars contribute to the enrichment of the interstellar medium. The material shed by Mira will eventually be incorporated into new stars and planets, showcasing the continuous cycle of stellar birth, death, and rebirth in our galaxy. The remarkable images of Mira's trail were captured by the Galaxy Evolution Explorer, also known as GALEX. This space telescope, launched by NASA in 2003, was designed to observe the universe in ultraviolet light. GALEX was particularly well suited for this task because it could detect the faint ultraviolet emissions from the trail of gas and dust left behind by Mira as it speeds through space. The telescope's sensitive instruments allowed astronomers to see a phenomenon that had never been observed before: a star leaving a visible wake in its path through the cosmos. This wake, stretching an astonishing 13 light-years behind Mira, is made up of material that the star has shed over tens of thousands of years. The GALEX observations revealed this trail to be glowing in ultraviolet light, likely due to interactions between the ejected material and the surrounding interstellar medium. This discovery was a testament to the power of space-based telescopes like GALEX, which can observe celestial objects in wavelengths of light that are blocked by Earth's atmosphere. The ability to see in ultraviolet allowed astronomers to witness this cosmic spectacle, providing new insights into stellar evolution and the ways stars interact with their galactic environment. Mira, a remarkable star in our galaxy, is creating a spectacle as it races through space. This aging red giant is shedding its outer layers, leaving behind a stunning trail of stellar debris that stretches an astonishing 13 light-years across the cosmos. To put this in perspective, if our solar system were the size of a grain of sand, Mira's tail would span the length of a football field. The reason for this extraordinary phenomenon lies in Mira's rapid movement through space and its current stage of stellar evolution. As Mira hurtles through the galaxy at about 90,000 miles per hour, it encounters the thin gas and dust that permeate interstellar space. This creates a bow shock in front of the star, similar to the wake of a boat moving through water. Behind this bow shock, Mira leaves a trail of material it has shed. Red giants like Mira are nearing the end of their lives, and they become unstable, pulsating and expelling their outer layers into space. This expelled material, rich in carbon and other elements forged within the star, forms the visible tail we observe. The combination of Mira's high speed, its phase of intense mass loss, and the interaction with the interstellar medium results in this cosmic spectacle. Mira's tail serves as a vivid reminder of the dynamic and ever-changing nature of stars, showcasing the processes that distribute elements across the galaxy and contribute to the cosmic cycle of stellar birth and death. The speed of material in a comet's tail varies depending on several factors, including the comet's distance from the Sun and the type of tail we're observing. Comets actually have two distinct tails, a dust tail and an ion tail. The dust tail, composed of tiny particles of rock and dust, typically moves away from the comet at speeds ranging from a few kilometers per second to tens of kilometers per second. This tail forms the familiar curved shape we often associate with comets, as the particles are pushed back by the pressure of sunlight. The ion tail, on the other hand, consists of ionized gases and moves much faster. These electrically charged particles can be accelerated by the solar wind to incredible velocities, sometimes reaching several hundred kilometers per second. In some cases, the material in the ion tail can achieve speeds of up to 1,000 kilometers per second. These high-speed particles in the comet's tail create a spectacular display as the comet approaches the Sun, with the tail stretching millions of kilometers into space. The varying speeds and compositions of the two tails contribute to the complex and beautiful phenomena we observe when comets grace our skies. Mira, a remarkable star in the constellation Cetus, leaves behind an extraordinary trail that sets it apart from other stellar phenomena. This cosmic wanderer, officially known as Omicron Ceti, travels through space at an astonishing speed of 130 kilometers per second, shedding material as it goes. The result is a colossal tail stretching an incredible 13 light-years in length, visible only in ultraviolet light. What makes Mira's trail truly unique is its composition and formation. Unlike the tails of comets or the debris left by some supernovae, Mira's tail consists of carbon, oxygen, and other elements crucial for the formation of new stars, planets, and even life itself. As Mira hurtles through the galaxy, it acts like a celestial sower, scattering the seeds of future cosmic bodies in its wake. The sheer scale of Mira's trail dwarfs many other stellar phenomena. For context, its 13 light-year length is about 20,000 times the distance from the Sun to Pluto. This vast expanse of material provides astronomers with an unprecedented opportunity to study stellar evolution and the enrichment of the interstellar medium. Mira's trail also stands out for its longevity and ongoing nature. While many stellar events like supernovae or gamma-ray bursts are relatively brief, Mira has been leaving its trail for tens of thousands of years and continues to do so. This constant process of material shedding and its interaction with the surrounding space offers a unique window into the dynamic relationships between stars and their environments, making Mira a stellar phenomenon that truly stands in a class of its own. Mira, a remarkable star in the constellation Cetus, leaves behind a spectacular trail as it races through space. This cosmic wake, stretching an astonishing 13 light-years, offers astronomers a unique opportunity to study stellar evolution and the interactions between stars and the interstellar medium. The trail of Mira consists of material shed by the star as it moves, creating a visible path of stellar debris. This material includes carbon, oxygen, and other elements crucial for the formation of new stars, planets, and even life. By analyzing the composition of this trail, scientists can gain insights into the internal processes of aging stars and how they enrich the galaxy with heavy elements. Furthermore, the shape and structure of Mira's trail provide valuable information about the star's movement through space and its interaction with surrounding gas and dust. The bow shock at the front of the trail, where the star's movement compresses the interstellar medium, offers clues about the density and composition of the space between stars. Studying Mira's trail also helps astronomers understand the life cycles of Sun-like stars and their eventual fate. As Mira is a red giant nearing the end of its life, its trail serves as a cosmic breadcrumb, tracing the star's journey and revealing the processes that occur during the later stages of stellar evolution. This knowledge is crucial for our understanding of stellar physics and the cosmic recycling of matter in our galaxy. Mira, a remarkable red giant star, leaves a stunning trail of stellar material as it hurtles through space. This cosmic wake stretches an astonishing 13 light-years behind the star, contributing significantly to the enrichment of the interstellar medium. As Mira races through the galaxy at about 87 miles per second, it sheds its outer layers, ejecting carbon, oxygen, and other elements forged in its core. This material forms a turbulent wake, much like the trail left by a boat moving through water. The ejected stellar matter mixes with the existing interstellar gas and dust, infusing it with heavier elements. This process of stellar enrichment is crucial for the evolution of the galaxy. The material shed by Mira and other similar stars provides the building blocks for future generations of stars and planets. Over time, this continuous injection of elements alters the composition of the interstellar medium, gradually increasing its metallicity, which is the proportion of elements heavier than hydrogen and helium. Moreover, the shock waves created by Mira's high-speed journey through space can trigger the formation of new stars in the interstellar medium. As the ejected material collides with surrounding gas clouds, it can compress them, potentially initiating the collapse that leads to the birth of new stars. Thus, Mira not only enriches the interstellar medium chemically, but also plays a role in shaping the ongoing stellar evolution in our galaxy. Mira, a remarkable star in the constellation Cetus, undergoes a fascinating process that causes it to shed material into space. This shedding is primarily driven by the star's pulsations and its advanced stage of stellar evolution. As a red giant star nearing the end of its life, Mira has expanded to an enormous size. Its outer layers have become less tightly bound by gravity, making them more susceptible to being pushed away from the star. The key to this material loss lies in Mira's nature as a variable star. It pulsates, alternately swelling and shrinking over a period of about 330 days. During each pulsation cycle, shock waves propagate through Mira's atmosphere. These waves, combined with the star's low surface gravity, help to lift material from the outer layers. Additionally, radiation pressure from the star's intense light output pushes against this lifted material, gradually driving it outward into space. This process of mass loss is further enhanced by dust formation in Mira's cool outer atmosphere. As gas is pushed outward and cools, it can condense into dust grains. These dust particles are more easily pushed by radiation pressure, acting like cosmic sails catching the star's light and carrying gas along with them as they drift into interstellar space. Mira, a remarkable red giant star in the constellation Cetus, is shedding an astonishing amount of material into space. Each year, this pulsating variable star loses approximately 100 millionth of the mass of our Sun. This might not sound like much at first, but for a star, it's an enormous amount of matter. To put this into perspective, the material Mira ejects annually would be enough to form an Earth-sized planet in just 10,000 years. This rapid loss of mass is creating a vast tail of stellar debris, stretching an incredible 13 light-years behind the star as it moves through space. This extraordinary rate of mass loss is a result of Mira's late stage of stellar evolution. As a red giant, Mira has expanded to hundreds of times the size of our Sun, with a tenuous outer atmosphere that's easily blown away by stellar winds and radiation pressure. The material ejected by Mira enriches the interstellar medium with heavy elements, contributing to the cosmic cycle of star formation and galactic evolution. This process showcases the crucial role that dying stars play in seeding the universe with the building blocks for future stars, planets, and potentially even life. Material is being ejected from Mira at an astonishing speed of approximately 300,000 kilometers per hour. This remarkable velocity is roughly equivalent to 1/4 the speed of light. Mira, also known as Omicron Ceti, is a pulsating variable star located about 400 light-years from Earth in the constellation Cetus. As Mira undergoes its regular pulsations, expanding and contracting over a period of about 11 months, it sheds vast amounts of material into space. This process, known as stellar wind, is common among aging stars, but particularly intense in Mira. The ejected material forms a tail stretching an incredible 13 light-years behind the star as it moves through space. The high-speed ejection of material from Mira is a result of complex interactions between the star's pulsations, its strong magnetic fields, and the intense radiation pressure from its surface. This phenomenon provides astronomers with valuable insights into the late stages of stellar evolution and the processes by which stars enrich the interstellar medium with heavy elements. Mira, a remarkable red giant star, races through the cosmos at an astonishing speed of 491,000 kilometers per hour. This rapid movement causes Mira to leave behind a spectacular trail of stellar material, stretching an incredible 13 light-years in length. As Mira hurtles through space, it sheds its outer layers, creating a wake of gas and dust that forms this elongated tail. The high velocity of Mira's journey plays a crucial role in shaping its trail. The faster the star moves, the more material it leaves behind, and the more pronounced the trail becomes. This speed also affects the distribution of the shed material, causing it to spread out over a vast distance rather than clustering close to the star. Interestingly, Mira's trail is not uniform. The intense ultraviolet radiation from the star ionizes the gas in its wake, causing it to glow. This ionization, combined with the star's speed, creates a bow shock at the leading edge of the trail, similar to the wake left by a boat moving through water. The bow shock compresses the interstellar medium ahead of Mira, further influencing the shape and composition of the trail. The study of Mira's high-speed movement and its resulting trail provides astronomers with valuable insights into stellar evolution, the interactions between stars and the interstellar medium, and the processes that shape our galaxy. This cosmic spectacle serves as a reminder of the dynamic and ever-changing nature of the universe, where even stars leave their mark as they journey through space. Mira's variability is a crucial factor in the formation of its remarkable trail. This red giant star, located about 400 light-years from Earth, pulsates over a period of about 330 days, dramatically changing in brightness as it does so. During each pulsation cycle, Mira expands and contracts, shedding layers of its outer atmosphere into space. This periodic shedding of material is directly linked to the star's variability. As Mira brightens and dims, it ejects more or less matter, creating a pattern of denser and less dense regions in its wake. The ejected material forms a comet-like tail, stretching an astonishing 13 light-years behind the star as it moves through space. The variability also affects the temperature and composition of the ejected material. During brighter phases, Mira expels hotter, more energetic particles, while in dimmer phases, the ejected material is cooler. This variation in temperature and composition contributes to the complex structure and appearance of the trail. Furthermore, the regular pulsations of Mira help to sustain the ongoing process of material ejection. Without this variability, the star would not be able to continually replenish its trail, which is constantly being shaped by its motion through the interstellar medium. Thus, Mira's variability is not just a contributing factor, but a fundamental driver in the formation and maintenance of its extraordinary cosmic wake. The interaction between Mira and its companion star plays a crucial role in creating the spectacular trail that stretches across the sky. Mira, a red giant star, is shedding its outer layers as it nears the end of its life. This process alone would create a modest stellar wind, but the presence of its companion dramatically amplifies the effect. As Mira orbits with its smaller, denser companion, likely a white dwarf, the gravitational forces between them cause Mira to pulsate more intensely. These pulsations increase the rate at which Mira loses mass, expelling more material into space. The companion star's gravity also pulls on this expelled material, shaping it into a spiral pattern as the two stars orbit each other. Furthermore, the companion star's motion through this expelled material creates a bow shock, much like the wave created by a ship moving through water. This bow shock compresses and heats the gas, making it more visible. As Mira moves through space at high speed, it leaves behind this processed material, forming the long, visible trail we observe. The combination of increased mass loss, gravitational shaping, and the bow shock effect results in a trail that is far more pronounced and visible than what Mira would produce on its own. This cosmic collaboration between Mira and its companion creates one of the most striking examples of stellar mass loss observable in our galaxy. The material in Mira's colossal trail exists in an extremely cold state. As this stellar debris stretches across vast distances of space, it cools significantly, reaching temperatures close to that of the cosmic microwave background. This background radiation permeates the universe and has a temperature of about 3 Kelvin. The particles and dust in Mira's tail have cooled to nearly this frigid level, making them some of the coldest known structures in space. Despite their low temperature, these particles are not completely inert. They still possess minute amounts of energy, allowing for some molecular interactions and potential for future star formation. This cold material, spread over a trail 13 light-years long, showcases the complex life cycle of stars and the redistribution of elements across the cosmos. The temperature gradient along Mira's tail provides valuable insights into stellar evolution and the behavior of matter in the harsh conditions of interstellar space. As astronomers study this unique structure, they gain a better understanding of how stars influence their galactic environments, even in their later stages of life. As we follow the trail extending from Mira, a remarkable red giant star, we observe fascinating changes in its composition. Near the star, the trail consists primarily of carbon-rich dust particles and molecules ejected from Mira's outer layers. These materials are the result of the star's pulsations and intense stellar winds, which expel matter into space. Moving further along the trail, we encounter a gradual shift in composition. The carbon-rich dust begins to mix with the surrounding interstellar medium, incorporating hydrogen and other elements prevalent in space. This mixing process creates a more diverse chemical environment, with the trail becoming less dominated by Mira's original stellar material. At even greater distances from Mira, the trail's composition becomes increasingly influenced by its interaction with the interstellar medium. Shock waves generated by the star's motion through space compress and heat the surrounding gas, leading to the formation of new molecular species. Additionally, ultraviolet radiation from other stars in the vicinity can break down some of the original molecules, further altering the trail's chemical makeup. As we reach the farthest extents of Mira's trail, stretching an astonishing 13 light-years, the composition becomes a complex blend of processed stellar material, interstellar gas, and dust. This evolving chemical tapestry not only tells the story of Mira's journey through space, but also provides valuable insights into the processes that shape the interstellar medium and contribute to the chemical enrichment of our galaxy. Mira's trail, stretching an astonishing 113 light-years behind the star, exhibits fascinating structures and patterns that offer insights into stellar evolution and galactic dynamics. The trail itself is composed of carbon, oxygen, and other elements shed by Mira as it moves through space at high velocity. One of the most notable features of Mira's trail is its bow shock structure at the leading edge. This arc-shaped region forms as Mira plows through the interstellar medium, compressing the gas and dust in front of it. Behind this bow shock, the trail shows a turbulent wake, with swirling eddies and filaments that twist and turn along its length. The trail also displays a segmented structure, with distinct clumps and knots of material spaced along its extent. These segments likely correspond to periodic episodes of increased mass loss from Mira, possibly tied to cycles in the star's pulsations or magnetic activity. Some researchers have even suggested that these segments might encode a history of Mira's journey through different regions of the galaxy. Importantly, the trail widens as it extends further from Mira, creating a cone-like shape. This widening occurs as the shed material interacts with and disperses into the surrounding interstellar medium. The patterns within Mira's trail not only reveal the star's history, but also provide a unique opportunity to study how stellar material mixes with and enriches the broader galactic environment. Mira, a remarkable star in the constellation Cetus, has been leaving behind an astonishing trail of stellar debris for approximately 30,000 years. This cosmic journey began when Mira started to shed its outer layers, a process typical for aging stars of its type. As Mira hurtles through space at an impressive speed of 130 kilometers per second, it continuously ejects material, forming a tail that stretches an incredible 13 light-years in length. The creation of this stellar trail is a testament to the dynamic nature of our galaxy. Mira's high velocity through the interstellar medium causes friction, compressing the gas in front of it while leaving a wake of material behind. This interaction between the star and its surrounding environment has resulted in the formation of a bow shock, similar to the wave created by a ship moving through water. What makes Mira's trail particularly fascinating is its visibility in ultraviolet light, as observed by NASA's Galaxy Evolution Explorer telescope. This discovery has provided astronomers with valuable insights into the life cycles of stars and the processes that distribute elements throughout the galaxy. The material shed by Mira enriches the interstellar medium with heavy elements, contributing to the formation of future stars and planets. Amateur astronomers can observe Mira, also known as Omicron Ceti, with relative ease due to its distinctive characteristics. This famous variable star, located in the constellation Cetus, undergoes dramatic changes in brightness over a period of about 11 months. At its peak, Mira can shine as brightly as a third-magnitude star, easily visible to the naked eye. However, during its dimmer phases, it fades to around 10th magnitude, requiring a small telescope to observe. To locate Mira, stargazers should first identify the constellation Cetus, which is visible in the night sky from autumn through winter in the northern hemisphere. Mira is positioned near the neck of the whale-like figure that Cetus represents. Using star charts or astronomy apps can greatly assist in pinpointing its exact location. The key to observing Mira is patience and persistence. Amateur astronomers should plan to observe the star regularly over several months to witness its full cycle of variability. This can be done by comparing Mira's brightness to nearby stars of known magnitude, a technique called magnitude estimation. By recording these observations over time, observers can create their own light curve of Mira's changing brightness. For those interested in more detailed study, photographing Mira through a telescope and using digital image processing can provide precise measurements of its brightness variations. This long-term observation project not only offers a fascinating glimpse into stellar evolution, but also allows amateur astronomers to contribute valuable data to the scientific community. Mira, also known as Omicron Ceti, is a fascinating variable star that offers a spectacular show for stargazers. The best time to observe Mira typically occurs during its peak brightness, which happens approximately once every 11 months. During this period, Mira can shine as brightly as a second or third magnitude star, making it visible to the naked eye. The exact timing of Mira's peak brightness varies from year to year, so astronomers and enthusiasts need to consult current astronomical almanacs or star charts for precise dates. Generally, Mira is most easily observable in the northern hemisphere during autumn and winter months, when the constellation Cetus, where Mira resides, is prominent in the night sky. It is worth noting that Mira spends most of its cycle at a much dimmer magnitude, often becoming too faint for the unaided eye to see. This dramatic change in brightness, from being barely visible to shining quite brightly, is what makes Mira such an intriguing target for observers. The star's name, which means wonderful or astonishing in Latin, is a testament to its remarkable variability. For those eager to witness this celestial spectacle, planning observations around the predicted maximum brightness and ensuring dark sky conditions will yield the best results. Regular monitoring of Mira throughout its cycle can provide a deeper appreciation of stellar variability and the dynamic nature of our universe. To observe Mira's variability, amateur astronomers can use relatively simple equipment. A pair of binoculars or a small telescope is sufficient to track the changes in brightness of this fascinating star. Mira, also known as Omicron Ceti, is a long-period variable star that dramatically changes its brightness over about 11 months. At its brightest, Mira can sometimes be seen with the naked eye, reaching a magnitude of around 3. However, when it dims, it fades to around magnitude 9 or 10, requiring optical aid to detect. This remarkable change in brightness makes Mira an excellent target for beginner stargazers and experienced observers alike. For those wanting to systematically study Mira's variability, a star chart of the constellation Cetus is essential. This chart helps locate Mira and compare its brightness to nearby stars of known magnitude. Some observers find it helpful to use a red flashlight to preserve their night vision while consulting charts. While not strictly necessary, keeping a log of observations over time allows astronomers to create their own light curve of Mira's cycle. This hands-on approach connects observers to the rhythms of the cosmos revealing the dynamic nature of stars that might otherwise appear unchanging to casual stargazers. Mira, the remarkable pulsating star in the constellation Cetus, leaves a stunning trail in space that stretches an incredible 13 light-years. This cosmic wake, however, is not visible to the naked eye or through standard amateur telescopes. The trail was discovered using specialized equipment aboard the Galaxy Evolution Explorer satellite, which detects ultraviolet light. While amateur astronomers cannot directly observe Mira's trail, they can still enjoy viewing the star itself. Mira is a variable star that changes in brightness over a period of about 11 months. At its peak, it can sometimes be seen with the naked eye, appearing as a reddish point of light. During its dimmer phases, it fades to a magnitude that requires binoculars or a small telescope to observe. For those interested in tracking Mira's brightness changes, a small telescope and patience are key. By observing the star regularly over several months, amateur astronomers can create their own light curves, documenting its fascinating cycle of brightening and dimming. This long-term observation project offers a tangible way to connect with the dynamic nature of stars and the ever-changing universe. Although the trail itself remains hidden from amateur equipment, the story of Mira and its cosmic wake serves as a powerful reminder of the complex and often invisible processes shaping our galaxy. It encourages us to look beyond what we can see and consider the broader, unseen impacts of stellar evolution on the space around us. Several space-based telescopes have been instrumental in studying Mira and its remarkable trail. The Galaxy Evolution Explorer, also known as GALEX, made a groundbreaking discovery in 2007 when it observed an astonishing 13 light-year-long tail trailing behind Mira. This ultraviolet space telescope revealed the true extent of Mira's influence on its surroundings, showing how the star leaves a wake of material as it travels through space. The Hubble Space Telescope has also played a crucial role in observing Mira. Its high-resolution capabilities have allowed astronomers to study the star's variability and the complex structures in its atmosphere. Hubble's observations have provided valuable insights into the processes of mass loss and the formation of dust around this evolved star. More recently, the Spitzer Space Telescope has contributed to our understanding of Mira by observing it in infrared light. This has allowed scientists to peer through the dust surrounding the star and study its temperature variations and the composition of its atmosphere. The James Webb Space Telescope, with its advanced infrared capabilities, is expected to provide even more detailed observations of Mira in the future, potentially revealing new aspects of its trail and its interaction with the interstellar medium. These space-based telescopes, each observing different wavelengths of light, have worked together to paint a comprehensive picture of Mira and its extraordinary trail. Their combined observations have revolutionized our understanding of stellar evolution and the impact that stars like Mira have on their galactic environment. Astronomers harness the power of spectroscopy to unravel the mysteries of Mira, a pulsating variable star that has captivated scientists for centuries. This powerful technique allows researchers to analyze the light emitted by Mira, breaking it down into its constituent wavelengths to reveal a wealth of information about the star's composition, temperature, and behavior. When astronomers point their telescopes at Mira, they collect its light and pass it through a spectrograph. This instrument separates the light into a spectrum, much like a prism creates a rainbow. The resulting spectral lines provide a unique fingerprint of the elements present in Mira's atmosphere. By studying these lines, scientists can identify the star's chemical makeup, including the presence of elements like hydrogen, helium, carbon, and oxygen. Spectroscopy also enables astronomers to measure Mira's temperature and track its changes over time. As the star pulsates, expanding and contracting over a period of about 330 days, its temperature fluctuates. These variations cause shifts in the spectral lines, allowing researchers to calculate the star's surface temperature at different stages of its cycle. Furthermore, spectroscopic observations reveal information about Mira's stellar winds and mass loss. By examining the Doppler shift of spectral lines, astronomers can determine the velocity of gas flowing away from the star. This data helps scientists understand how Mira sheds its outer layers, contributing to the enrichment of the interstellar medium and the cosmic cycle of stellar evolution. Observing Mira's trail presents several intriguing challenges for astronomers. The trail itself is an enormous structure stretching across 13 light-years of space, which is about 40,000 times the distance from Earth to the Sun. This vast scale makes it difficult to capture the entire trail in a single observation. The trail is composed primarily of carbon, oxygen, and other elements shed by Mira as it moves through space. These materials are incredibly diffuse, making the trail extremely faint and challenging to detect with conventional optical telescopes. Astronomers must rely on specialized instruments sensitive to ultraviolet light to observe the trail effectively. Another complication arises from Mira's variable nature. As a pulsating red giant star, Mira's brightness fluctuates dramatically over a period of about 11 months. This variability can affect the visibility and apparent structure of the trail, requiring astronomers to time their observations carefully. Lastly, the dynamic nature of the trail itself poses a challenge. As Mira moves through space, the trail is constantly evolving, with new material being shed and older material dissipating into the interstellar medium. This ongoing change requires repeated observations over extended periods to fully understand the trail's behavior and characteristics. Astronomers employ a combination of advanced techniques and specialized instruments to identify and study Mira's trail, setting it apart from other celestial phenomena. The trail, which stretches an astonishing 13 light-years behind the star Mira, is primarily visible in ultraviolet light. This unique characteristic allows scientists to use space-based telescopes like NASA's Galaxy Evolution Explorer to detect and analyze the trail with precision. The trail's distinctive bow-shock shape, caused by Mira's high-speed journey through space, serves as a key identifier. This shape is formed as the star plows through the interstellar medium, leaving behind a wake of material that has been heated and excited by the star's passage. The trail's consistent width and its direct connection to Mira's current position further distinguish it from other cosmic structures. Spectroscopic analysis plays a crucial role in confirming the trail's composition and origin. By examining the specific wavelengths of light emitted by the trail, astronomers can identify the presence of carbon, oxygen, and other elements consistent with material ejected from a star like Mira. This chemical fingerprint helps differentiate Mira's trail from other phenomena such as nebulae or remnants of supernova explosions. Time-lapse observations over several years enable astronomers to track the movement and evolution of the trail, providing additional evidence of its connection to Mira. By comparing images taken at different times, scientists can observe how the trail extends and changes, further confirming its unique nature and distinguishing it from static or differently evolving celestial objects. Astronomers have a keen interest in continuing to study Mira, the pulsating variable star that has captivated scientists for centuries. Future observations of Mira will likely involve a combination of ground-based and space-based telescopes, each offering unique insights into this fascinating stellar object. One planned observation involves using the James Webb Space Telescope to examine Mira in unprecedented detail. This powerful infrared observatory will allow researchers to peer through the dust surrounding Mira, potentially revealing new information about its structure and composition. The telescope's advanced instruments may also help scientists better understand the process of mass loss occurring in Mira, which is crucial for comprehending the late stages of stellar evolution. Additionally, long-term monitoring programs using both optical and radio telescopes are expected to continue. These observations will help astronomers track Mira's brightness variations over time, providing valuable data on its pulsation cycle and any potential changes in its behavior. Such long-term studies are essential for understanding how stars like Mira evolve and how they contribute to the enrichment of the interstellar medium. Furthermore, future observations may focus on studying Mira's binary companion and the interactions between the two stars. High-resolution imaging techniques and spectroscopic observations could reveal more about the nature of this binary system and how it influences Mira's evolution and behavior. Next-generation telescopes will revolutionize our observations of Mira and its remarkable trail. These advanced instruments will offer unprecedented sensitivity and resolution, allowing astronomers to capture finer details of this intriguing star system. With enhanced infrared capabilities, we will be able to peer through cosmic dust and gas more effectively, revealing the full extent of Mira's comet-like tail. These powerful telescopes will enable us to study the composition of Mira's trail with greater precision. We'll be able to identify and analyze the various elements and compounds present in the stellar material shed by Mira as it races through space. This detailed chemical analysis will provide valuable insights into the life cycle of stars and the enrichment of the interstellar medium. Furthermore, improved imaging techniques will allow us to track changes in Mira's trail over time, potentially revealing dynamic processes and interactions with the surrounding space. We might observe how the trail responds to variations in the interstellar medium or detect previously unseen structures within the tail itself. By combining observations from multiple next-generation telescopes, both ground-based and space-based, scientists will create a more comprehensive picture of Mira and its environment. This multi-wavelength approach will help us understand the physical mechanisms driving Mira's remarkable behavior and its impact on the surrounding cosmic neighborhood. Mira, also known as Omicron Ceti, is a remarkable star that significantly impacts the interstellar medium in its vicinity. This aging red giant star is undergoing a fascinating process of mass loss, ejecting vast amounts of material into space as it nears the end of its life. As Mira pulsates and expands, it sheds its outer layers, creating a stellar wind that carries gas and dust particles into the surrounding space. This outflow of material enriches the interstellar medium with heavy elements that were forged within the star during its lifetime. These elements, including carbon, oxygen, and nitrogen, become the building blocks for future generations of stars and planets. The interaction between Mira's stellar wind and the surrounding interstellar medium creates a bow shock, similar to the wake left by a boat moving through water. This bow shock compresses and heats the interstellar gas, potentially triggering the formation of new stars in the region. Additionally, the material ejected by Mira forms an extended tail stretching over 2 light-years behind the star as it moves through space. Mira's influence on the interstellar medium serves as a cosmic recycling process, redistributing stellar material and contributing to the ongoing cycle of star formation and galactic evolution. This phenomenon highlights the interconnectedness of stellar objects and the dynamic nature of our universe. Mira, a remarkable star in the constellation Cetus, exerts a profound influence on its surrounding space. This pulsating variable star, also known as Omicron Ceti, sheds an enormous amount of material into space as it travels through the galaxy. Mira leaves behind a comet-like tail stretching an astonishing 13 light-years in length, a distance that dwarfs many other stellar phenomena. This tail consists of carbon, oxygen, and other elements ejected from Mira over tens of thousands of years. As the star moves through space at about 87 miles per second, it creates a turbulent wake in the interstellar medium. This wake forms complex structures, including a bow shock ahead of the star and a trailing wake of gas and dust. The material shed by Mira enriches the interstellar medium, providing raw materials for future star formation. This process of stellar mass loss is crucial for the chemical evolution of galaxies, as it distributes heavy elements forged within stars throughout space. Mira's influence extends far beyond its immediate vicinity, contributing to the ongoing cycle of stellar birth, life, and death in our galaxy. Observations of Mira and its tail provide valuable insights into stellar evolution, particularly for stars in the late stages of their lives. By studying this cosmic phenomenon, astronomers gain a better understanding of how stars interact with their environment and how they contribute to the dynamic, ever-changing nature of our universe. Mira, the pulsating red giant star in the constellation Cetus, indeed influences its cosmic neighborhood. As Mira travels through space, it leaves behind a remarkable trail of stellar material, stretching over 13 light-years in length. This cosmic wake affects the interstellar medium, enriching it with carbon, oxygen, and other elements crucial for the formation of new stars and planets. The binary companion of Mira, known as Mira B, is directly impacted by the stellar wind from the primary star. This smaller white dwarf star accretes material from Mira, creating a complex interaction between the two celestial bodies. Their gravitational dance influences the shape and behavior of the surrounding gas and dust. Mira's powerful stellar wind also interacts with nearby interstellar clouds, potentially triggering the collapse of gas and dust to form new stars. This process, known as induced star formation, demonstrates how one star can influence the birth of others in its vicinity. While Mira's effects are most pronounced in its immediate surroundings, its influence extends further into space. The star's ultraviolet emissions and the shock waves created by its stellar wind can ionize and heat the interstellar medium, contributing to the overall dynamics of our galaxy's structure and evolution. Mira, also known as Omicron Ceti, is a remarkable star that plays a significant role in enriching its cosmic neighborhood. This aging red giant is in a phase of its life where it sheds vast amounts of material into space, contributing to the chemical diversity of its surroundings. As Mira pulsates, it expels its outer layers, creating a stellar wind that carries elements forged within the star's core. These elements include carbon, nitrogen, and oxygen, which are essential building blocks for life as we know it. The star's wind extends for light years, forming a tail-like structure that seeds the interstellar medium with these vital elements. What makes Mira particularly interesting is the rate at which it loses mass. Every year, it sheds enough material to form a new Earth, dispersing this matter across vast regions of space. This continuous process of stellar mass loss enriches the galactic environment, providing raw materials for future generations of stars and planets. The elements released by Mira will eventually mix with other interstellar gases and dust. Over time, this enriched material may collapse to form new stars, planets, and potentially even the complex molecules necessary for life. In this way, Mira and stars like it act as cosmic recyclers, ensuring the ongoing chemical evolution of our galaxy. Stars like Mira play a crucial role in galactic evolution, serving as cosmic recyclers and enrichers of the interstellar medium. Mira, also known as Omicron Ceti, is a prime example of a pulsating variable star in its late stages of life. These aging stars are vital contributors to the ongoing process of stellar birth and death that shapes our galaxy. As Mira-type stars pulsate, they shed their outer layers, expelling vast amounts of material into space. This ejected matter, rich in heavy elements forged within the star's core, becomes part of the raw material from which new stars and planets will form. The expelled gas and dust mix with the existing interstellar medium, gradually increasing its metallicity over time. This continuous enrichment process is fundamental to galactic chemical evolution. Each generation of stars born from this enriched material starts with a higher proportion of heavy elements, allowing for the formation of more complex structures and potentially life-supporting planets. The pulsations of Mira-like stars also create shock waves that help compress nearby gas clouds, potentially triggering new episodes of star formation. Moreover, the final stages of Mira-type stars contribute to the visible structure of galaxies. As they evolve into planetary nebulae, they create stunning, colorful displays visible across vast cosmic distances. These nebulae serve as markers of stellar evolution and contribute to the overall luminosity and appearance of their host galaxies. Mira, a remarkable red giant star, leaves a stunning trail as it journeys through space. This celestial wanderer interacts with the interstellar medium in fascinating ways, creating a cosmic spectacle that stretches for light years behind it. As Mira hurtles through space at high velocity, it plows through the sparse gas and dust that fill the vast regions between stars. This interaction creates a bull shock, similar to the wave that forms in front of a moving ship. The bull shock compresses and heats the interstellar material, causing it to glow and creating a visible arc ahead of the star. Behind Mira, the star leaves a wake of turbulence and disruption in the interstellar medium. This wake takes the form of a long, comet-like tail that extends for an astonishing 13 light years. The tail is composed of material shed by Mira itself, as well as interstellar gas that has been swept up and energized by the star's passage. The interaction between Mira's tail and the surrounding medium creates complex structures and patterns. Eddies and swirls form as the stellar wind from Mira mixes with the ambient interstellar gas. This turbulent wake serves as a cosmic laboratory, offering insights into the dynamics of stellar winds, the properties of the interstellar medium, and the processes that shape our galaxy on large scales. Mira, the remarkable variable star in the constellation Cetus, is indeed associated with an astonishing phenomenon as it hurtles through space. This celestial wanderer is moving at the incredible speed of 130 kilometers per second relative to the surrounding interstellar medium. At this velocity, Mira generates a spectacular bow shock wave in front of it, much like a boat creating a wake as it moves through water. This bow shock is a region where the stellar wind from Mira collides with the interstellar medium, creating a compressed and heated area of gas. The collision causes the interstellar material to pile up, forming a distinctive arc-shaped structure ahead of the star. Behind Mira, a turbulent wake stretches out for an astounding 13 light years, visible in ultraviolet light. The wake itself is a testament to the star's journey through space. As Mira moves, it sheds material, leaving behind a trail of carbon, oxygen, and other elements. This tail of stellar debris forms a vast, comet-like structure that astronomers have dubbed a bow-shock nebula. The material in this wake enriches the interstellar medium, potentially contributing to the formation of future stars and planets. Observations of Mira's bow shock and wake provide valuable insights into stellar evolution, the dynamics of the interstellar medium, and the processes by which stars distribute heavy elements throughout our galaxy. This cosmic spectacle serves as a vivid reminder of the dynamic and ever-changing nature of our universe, where even seemingly static stars are in constant motion, shaping the space around them. Mira, a remarkable red giant star, profoundly influences its surrounding space through intense radiation and material ejection. As Mira pulsates, it releases enormous amounts of energy across the electromagnetic spectrum, from infrared to ultraviolet. This radiation heats and ionizes nearby gas clouds, causing them to glow and creating a vibrant nebula around the star. The star's powerful stellar wind, driven by its radiation, expels vast quantities of material into space. This outflow of gas and dust forms an extended atmosphere around Mira, stretching far beyond what we typically consider the star's surface. The ejected material enriches the interstellar medium with heavy elements, contributing to the chemical evolution of the galaxy. Mira's radiation also interacts with its binary companion, Mira B. The intense energy from Mira causes material to flow from its extended atmosphere towards Mira B, forming an accretion disk. This transfer of mass and energy between the two stars creates a complex and dynamic system, influencing the evolution of both stellar objects. The effects of Mira's radiation extend even further into space. As the star moves through the galaxy, its powerful stellar wind collides with the surrounding interstellar medium, creating a bow shock. This phenomenon, visible in ultraviolet light, demonstrates the far-reaching impact of Mira's radiation on its galactic neighborhood, shaping the structure and composition of nearby space. As Mira journeys through space, its encounter with a nebula or molecular cloud would be a spectacular cosmic event. Mira, a pulsating red giant star, is already known for its extraordinary behavior, shedding vast amounts of material into space as it travels. When this unique star meets the diffuse gas and dust of a nebula or the dense molecular hydrogen of a cloud, the interaction would be both dramatic and scientifically intriguing. The powerful stellar wind from Mira would collide with the particles in the nebula or cloud, creating a bow shock ahead of the star. This shock wave would compress and heat the surrounding material, potentially triggering the formation of new stars in its wake. The compressed gas might also light up, creating a glowing arc that traces Mira's path through the cosmic structure. Simultaneously, the material Mira sheds would mix with the nebula or cloud, enriching it with heavier elements forged within the star. This process of stellar enrichment is crucial for the evolution of the galaxy, as it provides the building blocks for future generations of stars and planets. The mixing would also likely create complex chemical reactions, possibly forming new molecules and dust grains. The encounter would not leave Mira unchanged. As it plows through the denser medium, the star might accumulate some of the nebula or cloud material, potentially altering its own composition and behavior. This interaction could affect Mira's pulsations and mass loss rate, providing astronomers with a unique opportunity to study stellar evolution in a dynamic environment. Mira stars, also known as long-period variable stars, play a unique role in the cosmic tapestry. These pulsating red giants have a profound impact on their surroundings, quite different from their stellar counterparts. Unlike the steady, consistent output of main-sequence stars like our Sun, Mira variables undergo dramatic changes in brightness and size over periods of hundreds of days. The most striking feature of Mira stars is their prodigious mass loss. As they pulsate, these stars shed their outer layers, ejecting vast amounts of material into space. This process enriches the interstellar medium with heavy elements, contributing significantly to the chemical evolution of galaxies. In contrast, smaller stars like our Sun have a much more modest effect on their environment, releasing material primarily through solar wind. Mira stars also differ from more massive stars in their end-of-life impact. While supergiant stars explode as supernovae, dramatically altering their surroundings, Mira variables have a more subtle but longer-lasting influence. They gradually disperse their material over millions of years, creating extended envelopes of gas and dust that can span light years. These envelopes eventually mix with the interstellar medium, providing raw materials for future generations of stars and planets. Furthermore, the pulsations of Mira stars create shock waves that propagate through space, potentially triggering star formation in nearby molecular clouds. This ability to influence star formation on a local scale sets them apart from both smaller, less energetic stars and the more catastrophic effects of supernovae. Thus, Mira stars occupy a unique niche in stellar ecology, shaping their cosmic neighborhood through persistent, gentle processes rather than sudden, violent events. Mira holds a special place in the hearts of astrophysicists as a celestial pioneer. This pulsating variable star, also known as Omicron Ceti, was the first of its kind ever discovered. Its name, which means wonderful or astonishing in Latin, is a testament to the awe it inspired in early astronomers who observed its dramatic changes in brightness. What makes Mira truly remarkable is its cyclical nature. Over a period of about 332 days, it swings from being one of the brightest stars in the constellation Cetus to becoming nearly invisible to the naked eye. This extreme variability provides astrophysicists with a unique laboratory to study the late stages of stellar evolution. Mira serves as a prototype for an entire class of variable stars, now known as Mira variables. These are typically red giant stars nearing the end of their lives, shedding their outer layers as they pulsate. By studying Mira and its counterparts, scientists gain invaluable insights into the processes of stellar aging, mass loss, and the enrichment of the interstellar medium with heavy elements. Furthermore, Mira has surprised researchers with its comet-like tail, stretching an astonishing 13 light-years behind it as it hurtles through space. This discovery has opened new avenues for understanding stellar wind interactions with the interstellar medium, making Mira a continual source of fascination and scientific inquiry in the field of astrophysics. Mira, also known as Omicron Ceti, has been a celestial beacon for astronomers, shedding light on the fascinating later stages of stellar evolution. This pulsating variable star, discovered centuries ago, continues to reveal crucial information about the life cycles of stars similar to our Sun. Observations of Mira have shown us that as stars age, they can become unstable, dramatically changing in brightness over time. Mira's luminosity varies over a period of about 330 days, growing from barely visible to the naked eye to one of the brightest stars in its constellation. This pulsation is a key characteristic of stars in their red giant phase, a stage our own Sun will reach in several billion years. Mira has also taught us about mass loss in aging stars. As it pulsates, Mira ejects vast amounts of material into space, forming a tail of stellar debris that stretches for an astonishing 13 light-years. This process enriches the interstellar medium with heavy elements, contributing to the material from which new stars and planets may form. Furthermore, studying Mira has improved our understanding of binary star systems and their evolution. Mira A, the primary star, has a companion, Mira B, which accretes material from Mira A's stellar wind. This interaction between the two stars provides valuable insights into how binary systems evolve and influence each other over time, a common scenario in our galaxy. Mira, also known as Omicron Ceti, has played a crucial role in shaping our understanding of variable stars. This remarkable celestial object, located approximately 300 light-years from Earth, was first documented as a variable star in the late 16th century by Dutch astronomer David Fabricius. Mira's discovery marked a significant turning point in astronomy, challenging the long-held belief that stars were unchanging and eternal. As the prototype for an entire class of variable stars known as Mira variables, this pulsating red giant has provided astronomers with invaluable insights into stellar evolution and the final stages of a star's life. Mira variables are characterized by their long-period variability, typically ranging from 80 to 1,000 days, during which their brightness can fluctuate by several magnitudes. Observations of Mira have revealed that these variations are caused by pulsations in the star's outer layers. As the star expands and contracts, its surface temperature and size change, resulting in dramatic shifts in its luminosity. This pulsation mechanism, now understood to be common among many types of variable stars, has helped astronomers develop more accurate models of stellar interiors and atmospheres. Furthermore, studies of Mira and similar stars have enhanced our knowledge of mass loss in aging stars and the enrichment of the interstellar medium. As Mira sheds its outer layers, it contributes to the cosmic recycling process that forms new generations of stars and planets, deepening our understanding of galactic chemical evolution and the intricate connections between stars and their environments. Mira, a remarkable variable star in the constellation Cetus, has offered astronomers invaluable insights into the process of mass loss in aging stars. This red giant, whose brightness fluctuates dramatically over about 11 months, serves as a crucial model for understanding the late stages of stellar evolution. Observations of Mira have revealed that it is shedding its outer layers at an astonishing rate, losing mass equivalent to the Earth every 8 years. This rapid mass loss creates a vast, comet-like tail stretching an incredible 13 light-years behind the star as it moves through space. The discovery of this enormous tail, made possible by ultraviolet observations from the Galaxy Evolution Explorer spacecraft, has significantly expanded our understanding of how dying stars distribute elements into the interstellar medium. Furthermore, Mira has shown that mass loss in aging stars is not a smooth, continuous process, but can be episodic and highly variable. The star experiences periods of increased mass loss, which correlate with its brightness variations. These pulses of ejected material form concentric shells around the star, providing a historical record of its mass loss events. Mira has also demonstrated the importance of stellar pulsations in driving mass loss. As the star expands and contracts, shock waves propagate through its atmosphere, lifting material to altitudes where it can more easily escape the star's gravitational pull. This mechanism helps explain how stars can shed their outer layers even when their surface temperatures are relatively cool. Mira, also known as Omicron Ceti, serves as a stellar laboratory for astronomers, offering crucial insights into the later stages of stellar evolution. This pulsating variable star, located about 300 light-years from Earth, is a prime example of a red giant nearing the end of its life. By observing Mira, scientists can witness firsthand the processes that occur as stars transition from their main sequence phase to their final stages. One of the most valuable aspects of studying Mira is its predictable cycle of brightness changes. Over a period of about 330 days, Mira's luminosity fluctuates dramatically, sometimes becoming visible to the naked eye before fading to near invisibility. These pulsations are caused by the expansion and contraction of the star's outer layers, a phenomenon common to stars in this phase of their lives. By analyzing these pulsations, astronomers can better understand the internal structure and composition of aging stars. Mira also provides a glimpse into the future of our own Sun. As a star of similar mass to our Sun, Mira represents what our star might become in about 5 billion years. The star is actively shedding its outer layers, creating a tail of stellar material that stretches for an astonishing 13 light-years behind it. This process of mass loss is a key stage in stellar evolution, eventually leading to the formation of a planetary nebula with a white dwarf at its center. Furthermore, Mira is part of a binary system, offering astronomers the opportunity to study how companion stars interact during these late evolutionary stages. The interaction between Mira and its smaller, hotter companion provides valuable data on mass transfer and the influence of binary systems on stellar evolution. Through continued observation of Mira, scientists refine their models of stellar life cycles, enhancing our understanding of the cosmic processes that shape our universe. Mira, a red giant star in the constellation Cetus, offers us a fascinating glimpse into the potential future of our Sun. As a pulsating variable star about 350 light-years from Earth, Mira represents a stage of stellar evolution that our own star will likely experience billions of years from now. Currently, our Sun is a main sequence star, steadily fusing hydrogen into helium in its core. However, like Mira, it will eventually exhaust its central hydrogen fuel. When this happens, our Sun will expand dramatically, becoming a red giant similar to Mira. This expansion will cause its outer layers to cool and its color to shift towards red, much like we observe in Mira today. Mira also demonstrates the instability that characterizes this late stage of stellar life. It pulsates, varying in brightness over a period of about 11 months. These pulsations cause Mira to shed its outer layers, creating a stellar wind that disperses material into space. This process, which we witness in Mira, hints at how our Sun might enrich the surrounding space with heavy elements in its red giant phase. Studying Mira not only provides insights into our sun's distant future, but also helps us understand the crucial role that red giants play in cosmic evolution. These stars distribute elements forged in their interiors throughout the galaxy, contributing to the material that will form future stars and planets. Mira, also known as Omicron Ceti, has significantly expanded our understanding of binary star systems and variable stars. This remarkable celestial object consists of a red giant star and a smaller white dwarf companion, orbiting each other over a period of approximately 490 years. The primary star in the Mira system exhibits dramatic changes in brightness, varying from being visible to the naked eye to fading almost completely from view over a cycle of about 11 months. This pulsating behavior, characteristic of a class of variable stars now named Mira variables, has allowed astronomers to study the late stages of stellar evolution in unprecedented detail. Observations of Mira have revealed complex interactions between the two stars. The red giant is losing mass through stellar winds, some of which is captured by the white dwarf. This transfer of material between binary companions has provided crucial insights into how stars exchange matter and energy, influencing their evolution and the surrounding space environment. Furthermore, the Mira system has served as a laboratory for studying the formation of planetary nebulae. As the red giant continues to shed its outer layers, it will eventually expose its hot core, ionizing the surrounding gas and creating a spectacular nebula. This process, observed in various stages across different binary systems, has been better understood thanks to our long-term study of Mira. Mira, also known as Omicron Ceti, has been a pivotal star in the development of stellar physics. This remarkable celestial object, located approximately 300 light-years from Earth, is the prototype for a class of variable stars now known as Mira variables. These stars are characterized by their dramatic changes in brightness over long periods, typically ranging from 80 to 1,000 days. The discovery of Mira's variability in the late 16th century by David Fabricius marked a significant moment in astronomy. It challenged the prevailing notion that stars were fixed and unchanging, sparking a new era of stellar observation and theory. As astronomers continued to study Mira, they uncovered a wealth of information about the life cycles of stars, particularly in their later stages of evolution. Mira variables are now understood to be red giant stars nearing the end of their lives. They pulsate, expanding and contracting in size, which causes their dramatic changes in brightness. This pulsation mechanism, first proposed in the early 20th century, has been crucial in developing our understanding of stellar interiors and the physical processes that drive stellar evolution. The study of Mira has also contributed to our knowledge of mass loss in aging stars and the enrichment of the interstellar medium. As Mira sheds its outer layers, it releases material rich in heavy elements, which will eventually form new stars and planets. This process of stellar recycling is fundamental to the chemical evolution of galaxies, making Mira a key player in our understanding of cosmic chemistry and the cycle of stellar life and death. Studying Mira, a remarkable pulsating variable star, offers crucial insights into galactic chemistry and stellar evolution. As a red giant nearing the end of its life, Mira sheds vast amounts of material into space, enriching the interstellar medium with heavy elements. This process, known as stellar mass loss, is a key mechanism for distributing newly formed elements throughout the galaxy. Mira's regular pulsations cause it to dramatically change in brightness over a period of about 330 days. During each pulsation cycle, the star's outer layers expand and contract, dredging up elements from its core and expelling them into space. By analyzing the light from Mira, astronomers can determine the composition of these ejected materials, which include carbon, oxygen, and nitrogen. The study of Mira also helps us understand the life cycles of sun-like stars. As our own sun will eventually become a red giant similar to Mira, observing this star gives us a glimpse into the future of our solar system. The elements released by Mira and similar stars become the building blocks for new stars, planets, and potentially life itself, making these objects crucial links in the chain of galactic chemical evolution. Furthermore, the distinctive tail of material trailing behind Mira as it moves through space provides a unique opportunity to study how stellar winds interact with the interstellar medium. This interaction plays a vital role in shaping the chemical and physical properties of our galaxy, influencing star formation and the overall structure of the Milky Way. Mira, also known as Omicron Ceti, has been a source of fascinating discoveries for astronomers. This pulsating variable star, located about 300 light-years from Earth, has revealed several surprises during its centuries of observation. One of the most striking findings is Mira's comet-like tail, stretching an astonishing 13 light-years behind the star. This tail, discovered by NASA's Galaxy Evolution Explorer in 2007, consists of material shed by Mira as it moves through space. This discovery challenged our understanding of how stars interact with their surroundings and how they distribute elements throughout the galaxy. Another unexpected revelation came from studying Mira's companion star, Mira B. Initially thought to be a white dwarf, more recent observations suggest it might be a main sequence star. This finding has implications for our understanding of binary star systems and their evolution. Mira has also provided insights into the final stages of stellar life. Its pulsations and mass loss offer a preview of what our Sun might experience billions of years from now. These observations have helped refine models of stellar evolution, particularly for low to intermediate mass stars in their late stages of life. Mira, also known as Omicron Ceti, has captivated human observers for centuries. This pulsating variable star in the constellation Cetus has played a significant role in various cultures, often inspiring awe and sometimes fear. Ancient Chinese astronomers were among the first to document Mira's peculiar behavior. They referred to it as the guest star due to its seemingly unpredictable appearances and disappearances in the night sky. This mysterious celestial object was seen as a cosmic visitor, prompting careful observation and recording. In medieval Islamic astronomy, Mira was known as al-Sufi's wonderful star, named after the Persian astronomer Abd al-Rahman al-Sufi. His detailed observations of Mira's variability contributed significantly to our early understanding of this celestial phenomenon. European astronomers later built upon these observations, with David Fabricius officially documenting Mira's variability in 1696. The name Mira itself, meaning wonderful or astonishing in Latin, was bestowed by Johannes Hevelius in 1662. This name reflects the star's remarkable nature, changing from being barely visible to one of the brightest stars in the sky over a period of about 11 months. Across cultures, Mira's dramatic fluctuations have often been associated with omens or celestial messages, highlighting humanity's enduring fascination with the dynamic nature of our universe. Mira, also known as Omicron Ceti, has captivated human imagination for centuries. This pulsating variable star in the constellation Cetus has been the subject of various myths and legends across different cultures. In ancient Arabic astronomy, Mira was sometimes called al-Sadr al-Qitus, meaning the chest of the whale. This name reflects its position in the celestial sea monster Cetus. Some Arab astronomers also referred to it as the Wonderful or the Miraculous One, foreshadowing its later Latin name. The star's most famous legend comes from its Latin name, Mira, meaning wonderful or astonishing. This name was given by Johannes Hevelius in 1662, reflecting the star's remarkable behavior. Mira appears to vanish and reappear in the night sky over a period of about 11 months, a phenomenon that puzzled astronomers for centuries. In some Native American traditions, Mira's periodic brightening and fading was seen as a sign of changing seasons or impending important events. Its red color when bright led some cultures to associate it with fire or blood, often linking it to stories of celestial battles or divine manifestations. Ancient astronomers were fascinated by the mysterious behavior of Mira, a star that seemed to defy the constancy of the heavens. This red giant star in the constellation Cetus captured their attention with its peculiar habit of brightening and fading over time. To the naked eye, Mira appears to vanish and reappear in a cycle lasting about 11 months. This pattern puzzled observers who held the long-standing belief that the stars were fixed and unchanging. Some cultures saw Mira's fluctuations as a cosmic heartbeat or the winking of a celestial eye. In the late 16th century, Dutch astronomer David Fabricius first recorded Mira's variability, marking a significant moment in the history of stellar observation. He initially thought he had discovered a new star when Mira brightened, only to see it fade away months later. This led to Mira being dubbed the Wonderful, which is the meaning of its name in Latin. The discovery of Mira's variability challenged the prevailing Aristotelian view of an immutable cosmos. It paved the way for a new understanding of stellar evolution and the dynamic nature of the universe, inspiring future generations of astronomers to search for other variable stars and unravel the mysteries of stellar life cycles. The discovery of Mira's variability in the late 16th century marked a pivotal moment in astronomical history. This finding shattered the long-held belief that stars were unchanging, eternal beacons in the night sky. Mira, whose name means wonderful or astonishing in Latin, lives up to its moniker by dramatically changing its brightness over a period of about 11 months. This revelation opened astronomers' eyes to the dynamic nature of celestial objects. It sparked a new era of stellar observation and catalyzed the development of more precise instruments for measuring stellar brightness. The study of Mira led to the identification of an entire class of variable stars, now known as Mira variables, which are red giant stars nearing the end of their lives. The impact of Mira's discovery extended beyond stellar physics. It challenged the Aristotelian view of an unchanging celestial realm, contributing to the broader scientific revolution of the 16th and 17th centuries. This shift in understanding paved the way for future discoveries about stellar evolution, galactic structure, and the vast scale of the universe. Moreover, the study of Mira variables has provided valuable insights into the late stages of stellar life cycles. These stars serve as cosmic beacons, helping astronomers measure distances in space and understand the chemical enrichment of galaxies. The legacy of Mira's discovery continues to influence modern astrophysics, reminding us that the universe is far more dynamic and ever-changing than our ancestors ever imagined. Mira, also known as Omicron Ceti, has captured the imagination of artists and writers for centuries. This pulsating variable star, visible to the naked eye in the constellation Cetus, has been a source of fascination due to its dramatic changes in brightness. In literature, Mira has been featured in science fiction stories, often serving as a backdrop for tales of space exploration or alien civilizations. Authors have used its fluctuating nature as a metaphor for change and unpredictability in their narratives. Some writers have even speculated about potential life forms that could exist in such a dynamic stellar environment. Visual artists have depicted Mira in various forms, from traditional paintings to digital art. Its red hue and pulsating behavior have inspired artists to create dynamic, vibrant works that capture the star's ever-changing nature. In astronomical art, Mira is often portrayed with its companion star, showcasing the binary system's complex interactions. Mira has also found its way into music and poetry, with composers and poets drawing inspiration from its rhythmic brightness variations. These artistic interpretations often explore themes of cycles, rebirth, and the transient nature of existence, reflecting the star's own pattern of dimming and brightening over time. Mira, also known as Omicron Ceti, has been a crucial celestial object in the advancement of astronomical techniques. This pulsating variable star, discovered in the late 16th century, marked the beginning of our understanding of stars that change in brightness over time. Astronomers observed that Mira would periodically brighten and fade, a phenomenon that was previously unknown and challenged the prevailing notion of fixed, unchanging stars. The study of Mira led to the development of new observational methods and the creation of more precise instruments to measure stellar brightness. These advancements paved the way for the field of variable star astronomy, which has since become a cornerstone of modern astrophysics. By tracking Mira's light curve, scientists learned to determine stellar distances, masses, and compositions, techniques that are now applied to countless other stars. Mira has also played a significant role in our understanding of stellar evolution. As a red giant nearing the end of its life, Mira provides valuable insights into the late stages of stellar life cycles. Its pulsations and mass loss have helped astronomers refine models of how stars age and die, informing our broader understanding of galactic evolution. In recent years, observations of Mira have continued to yield surprises. Advanced telescopes have revealed a comet-like tail stretching an astonishing 13 light-years behind the star, showcasing the dynamic nature of stellar systems and prompting new questions about stellar wind interactions with the interstellar medium. This discovery demonstrates how Mira continues to drive innovation in astronomical techniques and expand our cosmic perspective. Our understanding of Mira has evolved dramatically as astronomical technology has improved. Originally discovered in the 16th century, Mira was long thought to be a single variable star that periodically brightened and dimmed. However, modern observations have revealed a far more complex and intriguing system. Advanced telescopes and imaging techniques have shown that Mira is actually a binary star system. It consists of a red giant star, Mira A, and a smaller companion, Mira B. This discovery has significantly altered our perception of Mira's behavior and characteristics. The interaction between these two stars creates a fascinating cosmic dance, with material flowing from Mira A to its companion. Space-based observatories like the Hubble Space Telescope have provided unprecedented views of Mira. These observations uncovered a surprising feature, a vast tail of cast-off stellar material stretching an astonishing 13 light-years behind the star. This comet-like tail, invisible to earlier astronomers, has given us new insights into stellar evolution and the impact of stars on their surrounding space. Spectroscopic advancements have allowed scientists to analyze Mira's composition and behavior in great detail. We now know that Mira A is a pulsating variable star, swelling and shrinking over a period of about 11 months. This pulsation, combined with its interaction with Mira B, creates a complex system that continues to intrigue astronomers and challenge our understanding of stellar physics. Mira, also known as Omicron Ceti, has captivated astronomers for centuries. This remarkable star in the constellation Cetus was first documented by David Fabricius in 1596. Fabricius noticed that Mira would periodically brighten and fade, a behavior unlike any other known star at the time. This discovery marked Mira as the first variable star ever recorded, opening up an entirely new field of stellar research. Johannes Holvarder made another significant contribution in 1638 when he determined Mira's period of variability to be approximately 11 months. This finding further cemented Mira's importance in astronomical studies. The star's name, which means wonderful or astonishing in Latin, was bestowed by Johannes Hevelius in 1662, reflecting the awe it inspired in early modern astronomers. In the 19th century, observations of Mira took a more scientific turn. Father Angelo Secchi, a pioneer in astronomical spectroscopy, studied Mira's spectrum in 1866. His work revealed that Mira's brightness variations were accompanied by changes in its spectral characteristics, providing crucial insights into the physical processes occurring within the star. More recent studies have continued to unveil Mira's secrets. In 2007, observations from the Galaxy Evolution Explorer spacecraft revealed a surprising 13 light-year-long tail of shed material trailing behind Mira as it moves through space. This discovery has expanded our understanding of how stars interact with their surrounding environment and contribute to the enrichment of the interstellar medium. Mira, also known as Omicron Ceti, has captivated astronomers and the public alike for centuries. This remarkable star, located in the constellation Cetus, has played a crucial role in sparking curiosity about the cosmos and advancing our understanding of stellar evolution. As one of the first variable stars ever discovered, Mira demonstrated that stars are not unchanging points of light, but dynamic, evolving objects. Its brightness fluctuates dramatically over a period of about 11 months, going from being easily visible to the naked eye to nearly disappearing from view. This striking behavior caught the attention of both professional and amateur astronomers, encouraging more people to observe the night sky and track celestial changes. The discovery of Mira-type variables, named after this prototype star, opened up new avenues of research in astrophysics. These pulsating red giant stars have become important cosmic yardsticks, helping scientists measure distances in the universe and understand the late stages of stellar life. This has not only advanced scientific knowledge, but also captured the imagination of the public, showcasing the dynamic nature of our universe. Mira continues to inspire interest in astronomy through its accessibility. Its regular cycle of brightening and dimming provides an excellent opportunity for amateur astronomers to contribute meaningful observations to the scientific community, fostering a sense of participation in cosmic discovery and encouraging more people to look up at the stars with wonder and curiosity. Mira, a remarkable star in the constellation Cetus, carries significance across various languages and cultures. In Latin, its name means wonderful or astonishing, aptly describing its variable brightness that puzzled early astronomers. Ancient Arabic stargazers called it Alomkar, meaning the whale, connecting it to the sea monster Cetus represents in Greek mythology. In Hindu astrology, Mira is associated with the nakshatra or lunar mansion called Chitra, symbolizing brilliance and creativity. This connection reflects the star's fluctuating luminosity, which can make it visible to the naked eye at its brightest and nearly invisible at its dimmest. Chinese astronomers included Mira in their neck mansion, part of the larger black tortoise of the North constellation. They viewed it as a celestial representation of the emperor's neck, highlighting its perceived importance in the cosmic order. The multicultural significance of Mira underscores how celestial objects often transcend linguistic and cultural boundaries, serving as common points of wonder and inspiration for diverse human societies throughout history. Mira, also known as Omicron Ceti, is a fascinating star that could indeed host a planetary system, though with some unique challenges. This red giant star is actually part of a binary system, paired with a smaller white dwarf companion. The dynamic nature of this stellar duo creates an intriguing environment for potential planets. As Mira pulsates and sheds its outer layers, it experiences significant changes in size and brightness over a period of about 330 days. This variability would have a profound impact on any planets orbiting the star. The intense stellar winds and radiation from Mira could potentially strip away the atmospheres of close-in planets, while also providing a rich source of material for planet formation in the surrounding space. The presence of the white dwarf companion further complicates the picture. Its gravitational influence would affect the stability of planetary orbits, potentially causing some to become unstable over time. However, this same gravitational dance might also create regions where planets could maintain stable orbits, perhaps in wide circuits around both stars. Recent observations have detected a protoplanetary disk around Mira, suggesting that planet formation may be ongoing in this system. While no planets have been confirmed yet, The existence of this disk indicates that the ingredients for planetary bodies are present. The Mira system serves as a compelling laboratory for studying how planets might form and evolve in the complex environments around aging stars. Mira, also known as Omicron Ceti, is a fascinating star that exhibits dramatic changes in brightness over time. This variability would have significant impacts on any planets that might orbit the star. As Mira pulsates, its size and luminosity fluctuate greatly, causing extreme variations in the amount of light and heat reaching its hypothetical planets. During its brightest phases, Mira can outshine its dimmer state by a factor of about 1,000. This means that planets in its system would experience intense periods of heating followed by long stretches of cooling. Such drastic temperature swings would make it challenging for life as we know it to develop or survive on these worlds. The changing size of Mira would also affect the gravitational forces experienced by orbiting planets. As the star expands and contracts, planets would be subjected to varying levels of tidal forces, potentially leading to increased volcanic activity and tectonic instability on rocky worlds. Furthermore, Mira is known to be losing mass through stellar winds. This ongoing process would gradually alter the star's gravitational influence over time, potentially causing shifts in planetary orbits. The stellar wind itself might also erode the atmospheres of nearby planets, further complicating the possibility of stable, life-supporting environments in the Mira system. Mira, a remarkable variable star in the constellation Cetus, poses significant challenges for exoplanet detection methods. This pulsating red giant star undergoes dramatic changes in brightness over a period of about 332 days, making it a complex target for planet hunters. The primary difficulty lies in Mira's variability. Most exoplanet detection techniques rely on precise, consistent measurements of a star's light or motion. The transit method, for instance, looks for tiny dips in a star's brightness as a planet passes in front of it. However, Mira's own fluctuations in luminosity can easily mask or mimic these planetary signals, making it extremely challenging to distinguish between stellar variability and potential planetary transits. Similarly, the radial velocity method, which detects the subtle wobble of a star caused by an orbiting planet's gravitational pull, faces complications with Mira. The star's pulsations and unstable atmosphere create their own complex patterns of motion, potentially overwhelming the delicate signals of orbiting planets. Furthermore, Mira's status as a red giant complicates matters. As stars like Mira expand in their later stages of life, they can engulf or disrupt the orbits of any inner planets, altering the planetary system's architecture. This makes it difficult to predict where planets might exist and how they might interact with the evolving star, adding another layer of complexity to the search for exoplanets around Mira and similar variable stars. Studying Mira, a remarkable pulsating variable star, offers valuable insights into the environments of exoplanets, particularly those orbiting aging stars. Mira serves as a cosmic laboratory, allowing astronomers to observe the complex interactions between a star in its late stages of evolution and its surrounding environment. As Mira pulsates, it sheds vast amounts of material into space, creating a rich, dynamic atmosphere around itself. This process mimics the conditions that many exoplanets might experience as their host stars age and expand. By examining the composition and behavior of the gas and dust ejected by Mira, scientists can better understand the potential atmospheric compositions of exoplanets in similar systems. Furthermore, the study of Mira helps astronomers refine their models of stellar evolution and its effects on planetary systems. As stars like Mira age, they can dramatically alter the habitable zones around them, potentially affecting the conditions on any orbiting planets. This knowledge is crucial for identifying and characterizing potentially habitable exoplanets, especially those around older stars. The observations of Mira also provide valuable data on the formation of complex molecules in space. These molecules, created in the cool, extended atmosphere of Mira, could be similar to those found in exoplanet atmospheres. By studying their formation and distribution around Mira, scientists can improve their ability to detect and interpret similar molecular signatures in exoplanet atmospheres, advancing our understanding of these distant worlds. Mira, also known as Omicron Ceti, offers valuable insights into the challenges of planetary habitability around variable stars. This pulsating red giant experiences dramatic changes in brightness over a period of about 332 days, swelling to nearly twice its size at its peak. These extreme fluctuations in stellar output have significant implications for potential planets orbiting Mira or similar variable stars. The habitable zone, where liquid water could exist on a planet's surface, would shift dramatically with each pulse. This constant movement of the habitable zone would likely create wildly unstable conditions on any orbiting worlds. Planets in such systems would face intense temperature swings, potentially causing their atmospheres to freeze and thaw repeatedly. This cycle could lead to rapid atmospheric loss, making it difficult for life as we know it to evolve or survive. Additionally, the intense stellar winds from Mira during its brighter phases could strip away planetary atmospheres over time. However, Mira also teaches us about the resilience and adaptability of potential life forms. Some scientists speculate that organisms might evolve to hibernate or migrate to survive these extreme cycles, much like creatures on Earth adapt to seasonal changes. While challenging, the study of Mira encourages us to broaden our understanding of habitability and consider more diverse environments where life might find a foothold in the universe. Mira, also known as Omicron Ceti, is a fascinating star that offers a glimpse into the potential fate of our own sun. As Mira evolves, its behavior could have profound effects on any planets orbiting it. Mira is a pulsating variable star, expanding and contracting over a period of about 330 days. During this cycle, its brightness can change dramatically, varying by up to 8 magnitudes. For planets in the Mira system, this would result in extreme fluctuations in the amount of light and heat they receive. As Mira continues to age, it will eventually become a red giant, swelling to hundreds of times its current size. This expansion could potentially engulf any inner planets, much like our Sun is expected to engulf Mercury and Venus in its red giant phase. Outer planets might survive, but would be subjected to intense solar radiation and stellar winds, potentially stripping away their atmospheres. The ultimate fate of Mira will be to shed its outer layers, forming a planetary nebula with a white dwarf at its center. Any surviving planets would then orbit this stellar remnant, bathed in the glow of the cooling white dwarf and the surrounding nebula. This transformation of their parent star would result in a completely altered planetary environment, unlike anything we observe in our solar system today. While Mira-type variables have been studied extensively, the search for exoplanets around these pulsating stars has been challenging. Mira variables are evolved red giant stars that undergo dramatic changes in brightness over long periods, typically ranging from about 100 to 1,000 days. This intrinsic variability makes it difficult to detect the subtle signals of orbiting planets using traditional methods like the transit or radial velocity techniques. Despite these challenges, astronomers have made some intriguing discoveries. In 2007, a team of researchers announced the possible detection of a planet orbiting the Mira variable star R Sculptoris. This potential exoplanet, if confirmed, would be a gas giant several times more massive than Jupiter, orbiting at a distance of about 1.5 times that between Earth and the Sun. However, it is important to note that this discovery remains controversial and has not been widely accepted by the astronomical community. The complex nature of Mira variables, with their pulsations and mass loss, makes it challenging to distinguish between planetary signals and stellar activity. Ongoing research and advancements in observational techniques may lead to more definitive discoveries in the future. As our understanding of these variable stars improves and our detection methods become more sophisticated, we may uncover more exoplanets in these intriguing stellar systems, potentially revealing new insights into planetary formation and evolution around evolved stars. Mira, a remarkable star system, presents unique challenges for planet formation due to its binary nature. This celestial duo consists of Mira A, a red giant star, and Mira B, a smaller companion believed to be a white dwarf. Their orbital dance creates a complex gravitational environment that significantly impacts the potential for planets to form and survive. The ever-changing gravitational forces in this binary system disrupt the stable orbits that planets typically require. As Mira A and Mira B circle each other, they create regions of instability where planet-forming materials are constantly jostled and scattered. This turbulent environment makes it difficult for dust and gas to coalesce into larger bodies, hindering the initial stages of planet formation. Furthermore, the pulsating nature of Mira A adds another layer of complexity. As it expands and contracts, it sheds vast amounts of material into space. This outflow of stellar matter can sweep away any nascent planets or protoplanetary disks that might be forming in the system. The intense stellar wind from Mira A also heats and disperses nearby gas and dust, further complicating the planet formation process. The presence of Mira B introduces additional challenges. Its gravitational influence can potentially capture material ejected from Mira A, forming an accretion disk around itself. This process not only competes with potential planet formation, but also creates a highly dynamic environment where stable planetary orbits are unlikely to persist. The interplay between these two stars makes Mira a fascinating but inhospitable place for planets to form and thrive. The sky on a planet orbiting Mira would be a spectacular and ever-changing display. Mira, also known as Omicron Ceti, is a binary star system consisting of a red giant and a white dwarf. The red giant, Mira A, is a pulsating variable star that dramatically changes in brightness over a period of about 11 months. From the surface of our hypothetical planet, Mira A would dominate the sky, appearing as an enormous deep red orb. Its size in the sky would dwarf our Sun as seen from Earth, potentially covering a significant portion of the visible sky. As Mira pulsates, the planet would experience dramatic shifts in illumination. During Mira's brightest phases, the entire landscape might be bathed in an intense, reddish light. Conversely, when Mira dims, the planet could be plunged into relative darkness. The white dwarf companion, Mira B, would likely appear as a bright, bluish-white point of light, creating a striking contrast with the red giant. Its position in the sky would change as it orbits Mira A, completing a circuit approximately every 500 years. This celestial dance would create a constantly evolving skyscape for any observers on the planet. Given the intense radiation and stellar winds from both stars, the planet's atmosphere might be filled with glowing gases, creating colorful aurora that could stretch across the entire sky. These ethereal lights would shift and dance, adding another layer of drama to this already awe-inspiring celestial view. Mira, a remarkable variable star system, offers valuable insights into our quest for extraterrestrial life. This binary system consists of a red giant star and a white dwarf companion, creating a cosmic environment that challenges our understanding of stellar evolution and planetary formation. The pulsating nature of Mira A, the red giant, results in periodic changes in its size and brightness. These pulsations cause the star to shed its outer layers, creating a trail of material in space. This process enriches the surrounding interstellar medium with heavy elements, which are crucial building blocks for planets and potentially life-supporting environments. Studying Mira helps astronomers understand how dying stars distribute elements throughout the galaxy, potentially seeding new star systems with the necessary ingredients for life. The complex interactions between Mira A and its white dwarf companion also provide clues about the long-term stability of binary systems, which could influence the habitability of any planets orbiting such stars. Furthermore, the unique conditions in the Mira system offer a natural laboratory for studying extreme environments. By observing how matter behaves in these conditions, scientists can refine their search parameters for potentially habitable exoplanets and develop more sophisticated models for detecting biosignatures in distant star systems. Mira, also known as Omicron Ceti, presents a fascinating case for potential advanced civilizations. This pulsating variable star, located about 350 light-years from Earth, undergoes dramatic changes in brightness over a period of about 11 months. These pulsations cause Mira to expand and contract, altering its temperature and luminosity significantly. The environment around Mira poses unique challenges for the development of life as we know it. The star's variability would create extreme fluctuations in the habitable zone, the region around a star where conditions might be suitable for life. Any planets orbiting Mira would experience dramatic swings in temperature and radiation levels, potentially making it difficult for complex life forms to evolve and thrive. However, we should not dismiss the possibility of advanced civilizations in such systems entirely. If life were to emerge, it might evolve to adapt to these cyclical changes, potentially developing unique biological or technological solutions to cope with the varying conditions. An advanced civilization might harness the star's pulsations for energy or develop protective measures against the periodic increases in stellar radiation. Interestingly, Mira is part of a binary system with a white dwarf companion. This additional star could provide another source of energy and stability, potentially offering more opportunities for life to develop. While the conditions around stars like Mira present significant challenges, the adaptability of life and the potential for advanced technology leave open the intriguing possibility of civilizations existing in these dynamic stellar environments. Mira, a remarkable pulsating variable star, exhibits dramatic changes in brightness over time. These fluctuations could have profound implications for any potential life-bearing planets in its vicinity. The star's luminosity varies by a factor of around 1,000 over a period of about 11 months, creating an environment of extreme and rapid changes. For any hypothetical worlds orbiting Mira, this variability would result in wildly fluctuating conditions. During Mira's brightest phases, planets would be bathed in intense radiation and heat, potentially causing severe climate shifts and atmospheric disruptions. Conversely, when Mira dims, these same planets might plunge into periods of relative darkness and cold. Such extreme oscillations in energy input would pose significant challenges for the development and sustainability of life as we know it. Organisms would need to evolve extraordinary adaptations to survive these regular dramatic shifts in their environment. They might require mechanisms to withstand both intense heat and cold, as well as the ability to cope with varying levels of radiation. However, it is important to note that life is remarkably adaptable. While Mira's variability presents formidable obstacles, it does not entirely preclude the possibility of life. Extremophiles on Earth have shown us that life can thrive in seemingly inhospitable conditions. The unique challenges posed by a variable star like Mira could potentially drive the evolution of highly specialized and resilient life forms, unlike anything we have encountered in our own solar system. Mira, also known as Omicron Ceti, has indeed been a target for SETA programs. This long-period variable star, located about 300 light-years from Earth, has attracted attention from astronomers and SETI researchers due to its unique characteristics and potential for harboring intelligent life. The SETI Institute has included Mira in its target list for radio observations using the Allen Telescope Array. This advanced radio telescope array, designed specifically for SETI research, has scanned Mira and its surrounding region for potential artificial signals that might indicate the presence of extraterrestrial intelligence. Mira is particularly interesting to SETI researchers because of its age and stability. As an asymptotic giant branch star, Mira is in a late stage of stellar evolution, which means any potential civilizations in its system would have had billions of years to develop. Additionally, the star's variability and its companion white dwarf create a complex and dynamic environment that could potentially support unique forms of life. While no conclusive evidence of extraterrestrial intelligence has been detected from Mira so far, it remains an intriguing target for ongoing SETI efforts. The star's proximity to Earth and its distinctive properties ensure that it will likely continue to be a focus of future searches for signs of intelligent life beyond our solar system. A civilization living around a star like Mira would face numerous extraordinary challenges. Mira, also known as Omicron Ceti, is a variable star that dramatically changes in brightness over time. This pulsating red giant expands and contracts, causing its luminosity to fluctuate by a factor of around 1,000 over a period of about 11 months. The most immediate challenge for any civilization would be adapting to these extreme changes in light and heat. During Mira's brightest phases, the intense radiation could potentially scorch the surfaces of nearby planets, while its dimmer periods might plunge these worlds into prolonged darkness and cold. This constant flux would make it difficult for life as we know it to evolve and thrive. Furthermore, Mira is shedding its outer layers, losing mass at a significant rate. This stellar wind creates a comet-like tail stretching over 13 light-years behind the star. Any planets orbiting Mira would be bombarded by this outflow of stellar material, potentially stripping away their atmospheres over time. Lastly, Mira is nearing the end of its life cycle and will eventually shed its outer layers completely, becoming a white dwarf. This inevitable fate would pose an existential threat to any civilization in its system, necessitating advanced technology for long-term survival or interstellar migration. An advanced civilization seeking to harness the energy of a Mira-type star would face unique challenges and opportunities. Mira variables are pulsating red giant stars that dramatically change in brightness over long periods, typically ranging from about 80 to 1,000 days. These stars offer an intriguing energy source due to their immense size and variable output. During their brightest phases, Mira stars can radiate up to 10,000 times more energy than our Sun. This tremendous energy output could be captured using vast arrays of solar collectors or advanced stellar-scale engineering projects. One potential method for energy extraction could involve constructing a partial Dyson sphere or swarm around the star. This megastructure would consist of millions of individual collectors orbiting the Mira variable, each designed to withstand the intense radiation and gravitational forces. The collectors would need to be highly adaptable, capable of adjusting their positions and energy absorption rates to accommodate the star's pulsations and changing output. Another approach might involve tapping into the powerful stellar winds emitted by Mira variables. These stars shed large amounts of material into space, creating extended envelopes of gas and dust. Advanced civilizations could potentially develop technologies to collect and process this ejected matter, converting it into usable energy or resources for interstellar colonization and engineering projects. Mira, the remarkable red giant star, leaves behind a stunning trail of stellar material as it races through space. This cosmic wake, stretching an astonishing 13 light-years, presents an intriguing possibility for interstellar communication. The trail itself acts as a vast, naturally occurring signal in space, visible across immense distances. The concept of using Mira's trail for communication hinges on the idea of manipulating or modulating this existing cosmic phenomenon. Advanced civilizations could potentially alter the trail's composition or structure to encode messages. These alterations might involve changing the density of the material, its chemical makeup, or even creating patterns within the trail itself. One advantage of using Mira's trail for communication is its longevity and visibility. The trail persists for thousands of years, providing ample time for messages to be detected and decoded. Additionally, its scale makes it observable from vast distances, potentially allowing for communication across significant portions of our galaxy. However, practical challenges abound. The timescales involved in creating and altering such a trail are enormous, and the energy required to manipulate it would be staggering. Moreover, decoding any potential messages would require advanced technology and a deep understanding of stellar physics. While Mira's trail remains a fascinating cosmic feature, its use as a communication medium remains firmly in the realm of speculation and science fiction for now. Studying stars like Mira provides valuable insights that aid our search for habitable worlds in several ways. Mira is a pulsating variable star, meaning its brightness changes over time. This variability allows astronomers to measure the star's size, mass, and composition with great precision. These characteristics are crucial in understanding stellar evolution and the potential for planets to form and survive around different types of stars. Mira-type stars are typically old, cool red giants nearing the end of their lives. By studying these stars, we gain a better understanding of the later stages of stellar evolution. This knowledge helps us predict how long stars like our Sun will remain stable and capable of supporting life on their planets. It also informs our search for habitable worlds by indicating which stars are more likely to have planets in their habitable zones for extended periods. Furthermore, Mira stars often eject large amounts of material into space, enriching the interstellar medium with heavy elements. These elements are essential for forming rocky planets and the building blocks of life. By studying the composition of material ejected by Mira-type stars, we can better understand the chemical evolution of galaxies and the potential for planet formation in different cosmic environments. The pulsations of Mira-type stars also teach us about stellar atmospheres and their interactions with potential planets. This information is crucial for assessing the habitability of worlds around various types of stars, as stellar activity and radiation can significantly impact planetary atmospheres and surface conditions. By applying this knowledge to our search for habitable worlds, we can refine our criteria and focus our efforts on the most promising star systems. When exploring Mira-like systems for potential biosignatures, scientists focus on several key indicators that could suggest the presence of life. Mira-type stars, being cool red giants, present unique challenges and opportunities in the search for extraterrestrial life. One promising biosignature in these systems could be the presence of methane in a planet's atmosphere. Methane is a gas that, on Earth, is primarily produced by living organisms. In a Mira-like system, detecting significant amounts of methane alongside oxygen could be a compelling sign of biological activity. Another biosignature to consider is the presence of water vapor. While not exclusively indicative of life, water is essential for life as we know it. In the extended habitable zones of Mira-type stars, planets with the right conditions might harbor liquid water on their surfaces, making them prime candidates for further investigation. Researchers also look for signs of photosynthesis or similar light harvesting processes. In Mira-like systems, where the star emits most of its light in the infrared spectrum, we might search for pigments or chemical signatures that indicate organisms have adapted to use this type of light for energy. This could manifest as unique absorption patterns in the planet's atmosphere or surface reflectance. Mira, also known as Omicron Ceti, is a fascinating binary star system located about 350 light-years from Earth. This system consists of Mira A, a red giant star, and Mira B, a smaller companion that is likely a white dwarf. The binary nature of Mira significantly impacts the potential for life in its system in several ways. Firstly, the presence of two stars creates a complex and dynamic gravitational environment. This instability makes it challenging for planets to maintain stable orbits, which is crucial for the development and sustenance of life. Planets in this system would likely experience extreme temperature fluctuations as they move between the two stars, creating conditions too volatile for life as we know it to thrive. Moreover, Mira A is a variable star that pulsates, dramatically changing in brightness over a period of about 330 days. These pulsations cause Mira A to shed its outer layers, creating a stellar wind that extends far into space. This wind, combined with the radiation from both stars, would likely strip away the atmospheres of any planets in the system, making it inhospitable for life. The age and evolutionary stage of Mira A also play a role in the system's habitability. As a red giant, Mira A has already moved beyond its main sequence phase, during which stable conditions conducive to life might have existed. Any planets that may have harbored life earlier in the star's history would now be exposed to intense heat and radiation, effectively ending any chance for life to persist. Mira, also known as Omicron Ceti, offers valuable insights into the long-term evolution of stars and their potential impact on planetary habitability. This pulsating variable star, located about 350 light-years from Earth, is in the late stages of its life cycle, having transitioned from a star similar to our Sun into a red giant. As Mira expands and contracts, it sheds vast amounts of material into space, creating a tail of debris that stretches for an astonishing 13 light-years behind it. This process of mass loss dramatically alters the star's immediate environment, potentially affecting any planets that may have once orbited it. Studying Mira helps astronomers understand how stars like our Sun will evolve over billions of years. As stars age and expand into red giants, they can engulf their inner planets and significantly alter the habitable zone, the region around a star where conditions might be suitable for life. This shifting habitable zone could render previously life-supporting planets too hot or too cold for life as we know it. Furthermore, Mira's pulsations and mass loss demonstrate how aging stars can distribute heavy elements throughout their stellar neighborhood. These elements, crucial for planet formation and potential life, enrich the surrounding space and could contribute to the development of new planetary systems in the future. By examining Mira, we gain crucial knowledge about stellar life cycles and their long-term effects on planetary habitability, helping us better understand the past and future of our own solar system.